Hello, and welcome to The Sleepy Scientist. I'm glad you've joined me tonight. Before we drift away to the red sands of Mars, let me ask, where in the world are you listening from right now? Whether you're curled up in bed, lying back on the sofa, or sitting in a quiet corner somewhere, I'm happy you're here. If you enjoy these journeys and would like to join me for more, could I kindly ask you to give this video a like? And if you haven't already, please do subscribe. It's the simplest way to travel with me again, and while you're at it, turn on notifications so you'll know exactly when our next adventure begins. It's a small thing for you, but it means the world to me, and it keeps this little community of calm curiosity growing. And to those of you already subscribed, thank you. You're the reason these voyages keep setting sail. I'll do my best to make this gentle enough to ease you into rest. Though, I must confess, there's always the risk that I make Mars sound just a little too fascinating. If that happens and you find yourself wide awake, well, at least you'll be lying there with a head full of cosmic facts to ponder. So, as we begin, let me ask you this. What if the quietest place in the solar system is also one of the most mysterious? Mars, our small rust-coloured neighbour, has been a source of wonder for as long as humans have looked to the night sky. Its steady glow has guided ancient astronomers, inspired myths of gods and warriors, and stirred dreams of life beyond Earth. Yet behind that familiar red shimmer lies a world far stranger and more beautiful than its distant appearance suggests. In the chapters ahead we will not rush. Instead, we will linger, on the frost that creeps across Martian dunes at dawn, on the whisper of wind that stirs the dust, and on the silent scars left by ancient rivers. We will wander through canyons so vast they could swallow entire countries, climb mountains that stretch nearly to the edge of space, and pause to listen to the thin, delicate air sighing over stone. Along the way, we'll uncover the science of how this world came to be, how it once may have been blue with oceans, how it lost the shield that guarded its skies, and how the same forces that shaped it can teach us about our own fragile planet. There will be stories of exploration too, machines with wheels and wings, built to endure the cold, to taste the soil, and to send back images of landscapes no human has yet walked. This is not just the story of a planet, it is the story of a companion, a quiet, steady presence in the dark, and of our deep, persistent longing to reach it. So settle in, and let us drift together toward the red horizon, where every grain of dust holds the memory of a world that might have been. If you were to step outside on a crisp, clear night and look up, Mars would appear as a small but steady point of rusty light against the darkness. Unlike the cold, white sparkle of most stars, it glows with a subtle warmth, a red-orange ember burning quietly millions of kilometres away. That colour is what first set it apart for ancient sky watchers, who noticed not only its hue but also its behaviour. Most of the lights in the night sky seemed fixed in their positions, wheeling overhead together as the hours passed. But a few, the planets, wandered. Mars was one of these wanderers. Long before telescopes, people noticed that this reddish wanderer did not follow the same steady path each night. For much of the year, it would drift eastward against the backdrop of stars, but then slowly it would appear to hesitate, stop and move backward, westward, before resuming its original course. This strange loop is called retrograde motion, and it was deeply puzzling for early observers. To the naked eye it seemed almost deliberate, as if Mars had a mind of its own, and was pausing mid-journey to reconsider its route. Ancient civilizations gave Mars names and stories that reflected its unusual character. The Babylonians called it Nergal, after their god of war and destruction. The Greeks named it Ares, and the Romans followed suit with Mars, their own war god. The red tint naturally linked the planet to blood and battle, even though in reality its deserts are far too cold and empty for such drama. Yet the connection stuck, and in every culture that tracked its movements, Mars was a figure of significance, a celestial actor with a role to play. The retrograde loops it traced in the sky were one of astronomy's oldest mysteries. In the geocentric model, the belief that Earth sat at the centre of the universe, this behaviour required some creative explanations. Claudius Ptolemy, a Greek-Egyptian astronomer of the 2nd century, came up with an elaborate system of circles within circles called epicycles. According to his model, Mars travelled along a small circle, while that circle itself moved along a larger path around Earth. It was elegant in its own way and matched the observations reasonably well, but it was also a mathematical patch on a deeper misunderstanding. The true explanation would come more than a millennium later, when Nicholas Copernicus revived the idea that the Sun, not Earth, was at the centre of the planetary system. In a heliocentric model, retrograde motion is not an oddity of Mars itself, but a matter of perspective. As Earth catches up to and overtakes Mars in its orbit, the red planet appears to move backward briefly, much like how a slower car on the highway seems to drift backward as you pass it. Once understood, the motion was no longer mysterious, but it remained just as beautiful to watch. Even without modern equipment, ancient astronomers were remarkably skilled at tracking Mars. The Mayans could predict its position years in advance, and in India, precise records were kept of its loops across the constellations. These observations weren't idle curiosity. They were often linked to calendars, navigation, and even agriculture. A planet's position could be considered an omen, guiding decisions in war or politics. For Mars, with its fiery hue, such omens were rarely gentle ones. Then, in the early 17th century, Galileo Galilei turned his telescope toward Mars. His instrument was modest by modern standards, little more than a tube with a few carefully ground lenses, yet it transformed Mars from a wandering light into a small disk. This was proof that Mars was not a star but a world, a place with a surface, size, and shape. Galileo could not see its details clearly, but the revelation that it was tangible was enough to challenge centuries of assumptions. A few decades later, the Dutch astronomer Christian Huygens used a better telescope to make the first known drawing of a surface feature on Mars, a dark triangular region now called Syrtis Major. By watching its position change over time, he estimated the length of a Martian day in just over 24 hours, remarkably close to the modern value. The thought that Mars experienced day and night much like Earth did only deepened the sense of connection between our two worlds. Over the centuries that followed, telescopes grew more powerful, and Mars revealed more of its character. Astronomers mapped its polar caps, saw the seasonal changes in their size, and speculated that these were made of water ice, much like Earth's poles. Such findings fed the imagination. If Mars had ice, if it had a day length similar to ours, and if its surface showed shifting patterns, perhaps it also had life. By the late 19th century, some observers, like Percival Lowell, believed they saw straight lines crisscrossing its surface. Canals, he thought, built by intelligent beings to carry water from the poles to the equator. It was an appealing idea, even if it later turned out to be a trick of the eye and the mind. But long before those telescopic illusions, Mars had already captured human imagination, simply by the way it moved in the night sky. Its steady brightness and its slow, looping dance made it stand out from all other points of light. It was both familiar and foreign, always there in the heavens, but clearly not like the stars. Watching it glide through the constellations, vanish into the sun's glare, and reappear months later gave a sense of rhythm, of cosmic breathing, that tied our nights to the clockwork of the solar system. In that way, Mars taught us something important before we ever set foot on it, or sent machines to its surface. The universe is not static. Worlds move, shift, and follow paths that, while predictable, are far from simple. And in learning to understand the path of one small red planet, we began to understand our own place among them. Around 4.5 billion years ago, the solar system was not the quiet, ordered place we see today. It was a chaotic disk of gas, dust, and ice, circling a young sun that shone a little less brightly than it does now. Within this swirling cloud, tiny grains collided, stuck together, and gradually grew into clumps called planetesimals. Those clumps merged into larger and larger bodies, each gathering more material through gravity's gentle but relentless. Mars was born in this crowded nursery, in a region between the Sun and what would eventually become the asteroid belt. The material there was sparser than in Earth's neighbourhood, which meant Mars had fewer building blocks to draw from. This scarcity shaped its fate. Mars ended up only about half the diameter of Earth and with roughly 1/10 of its mass. It was a small planet in a solar system of giants and medium-sized worlds. Size, in planetary terms, is more than a matter of ego. A larger planet can hold on to its internal heat for longer, keeping its molten core churning and generating a strong magnetic field. That field acts like a shield, protecting the atmosphere from being stripped away by the solar wind. A smaller planet like Mars cools faster, its internal dynamo slowing and eventually shutting down. Without a protective magnetic field, the atmosphere becomes vulnerable, and over time it thins. In Mars's case, this process set the stage for a transformation from a potentially wetter, warmer world to the cold, dry desert we see today. In its youth, Mars was anything but still. Volcanoes erupted across its surface, pouring out lava that reshaped the land. In fact, some of these volcanoes would grow to be the largest in the entire solar system. Olympus Mons, the most famous of them all, rises nearly 3 times higher than Mount Everest and sprawls across an area the size of France. Such immense size was possible because Mars, unlike Earth, has no tectonic plates shifting beneath its crust. On Earth, volcanic hotspots move relative to the surface, creating chains of volcanoes like the Hawaiian Islands. On Mars, the crust stayed fixed over its hotspots, allowing lava to pile up in the same place for millions of years. The early Martian surface also bore the marks of colossal impacts. In the first few 100 million years of the solar system's history, asteroid collisions were frequent and often catastrophic. One of the most dramatic examples is the Borealis Basin in Mars' northern hemisphere, a massive lowland thought to have been carved out by a single gigantic impact. If the theory is correct, it was the kind of collision that could reshape an entire hemisphere in one violent instant. Elsewhere, craters overlapped craters, some later softened or buried by lava flows, others left as sharp scars in the rock. These impacts, though destructive, also played a role in shaping the planet's geology and perhaps even its climate. Large collisions can release enough energy to temporarily heat the atmosphere and melt surface ice, leading to periods of flowing water. In Mars's early days, rivers and lakes carved channels and valleys, leaving behind patterns we can still see from orbit. These watery episodes may have been brief and intermittent, but they hint at a world that was not always the frozen desert it is now. Beneath the surface, Mars' interior was evolving. Early on, the heat from radioactive decay and leftover energy from its formation kept the mantle partially molten. Magma rose, cooled, and solidified into layers, building the planet's crust. Over time, as the heat faded, the mantle stiffened and the crust became thicker and more rigid. Without the slow churn of tectonic activity to recycle rock and release gases, Mars's surface features became remarkably well preserved. On Earth, landscapes are constantly erased and remade, but on Mars, a riverbed from billions of years ago can remain almost unchanged. The lack of tectonics also meant that Mars volcanoes eventually went dormant. We don't know exactly when the last major eruption took place, but evidence suggests that volcanic activity persisted for much longer than once believed, perhaps as recently as a few million years ago. That's geologically recent, the planetary equivalent of a lingering ember in an otherwise cooled fire. In the first billion years of its life, Mars may have had a thicker atmosphere, enough to keep water liquid on the surface for extended periods. If so, it was a climate very different from the one we know today, with clouds, rain, and even snow. Over time, though, as the magnetic field weakened and the atmosphere was steadily stripped away by the solar wind, Mars lost much of its capacity to hold warmth. The planet's once active hydrological cycle slowed. then all but stopped. Water retreated underground or froze at the poles, leaving the familiar dry landscapes we see in modern images. While this cooling and drying marked the end of one chapter in Mars's history, it preserved another. Many of the planet's oldest features remain frozen in time, providing a geological record far more complete than Earth's. Ancient river deltas, lava plains, and impact craters offer scientists a kind of planetary scrapbook, each page telling a story from an era long gone. Today, when we look at Mars through the eyes of orbiters and rovers, we're seeing the end result of these early forces: the violence of impacts, the power of volcanoes, the slow loss of heat and atmosphere. Yet these same forces, billions of years ago, might have created conditions where life could have taken hold, if only briefly. Whether it did or not is still one of the most intriguing questions in planetary science. Mars's small size may have sealed its fate as a cold, airless desert, but it also ensured that its surface would remain a remarkably faithful witness to its own past. Every dune, plateau, and crater holds a fragment of that history waiting for us to read it. The planet may no longer be geologically active on a grand scale, but in the patterns etched into its surface, the echoes of its fiery youth still remain. If you were to hover above Mars in its earliest days, you might have been surprised by how familiar parts of it looked. Instead of the bone-dry deserts and rust-red dust we know now, you would have seen winding rivers, scattered lakes, and perhaps even broad inland seas. The planet was still smaller, colder, and drier than Earth, but for a time it appears to have been wet enough for water to flow freely across its surface. That brief watery chapter left its mark in stone, a kind of ancient graffiti etched by the movement of liquid over rock. The first real hints of this story came from spacecraft images in the 1970s. NASA's Mariner missions, followed by the Viking orbiters, showed networks of channels that looked remarkably like dried-up riverbeds on Earth. Some stretched for hundreds of kilometers, branching into tributaries before merging into wider valleys. These were not the random scars of erosion caused by wind alone. They were shaped in the familiar patterns of water finding its way downhill. It was like looking at a desert on Earth where the rivers had simply vanished, leaving only the empty channels behind. Closer examination revealed several types of these features. Some were narrow, branching valleys resembling the ones carved by rainwater on our planet. Others were deep, straight troughs, possibly formed by sudden floods or the collapse of underground water systems. Then there were the immense outflow channels, suggesting catastrophic releases of water from beneath the surface, events that may have reshaped entire regions in a matter of days. Alongside these channels are ancient deltas, where a river once slowed and spread out into a fan of sediment before meeting a larger body of water. One of the most famous examples is in Jezero Crater, where NASA's Perseverance rover is now exploring. From orbit, the delta's shape is unmistakable, the same wedge-like formation we see where rivers meet lakes or seas on Earth. This is a signature of calm, standing water, a place where sediment could settle and build up over time. If Mars ever supported life, a delta like this would have been a prime location for it, sheltered and rich in minerals. Minerals themselves tell another part of the tale. On Earth, certain minerals form only in the presence of liquid water. Clays, for instance, require prolonged contact with water to develop. Sulfates can crystallize from evaporating water bodies, leaving behind crusts and deposits. Thanks to orbiters equipped with spectrometers, scientists have detected these minerals scattered across ancient Martian terrains. Their presence is like a chemical fingerprint, proving that water was once there, interacting with the rock over long stretches of time. The distribution of these minerals also hints at changes in Mars' environment. In some areas, clays dominate, suggesting that the early water was relatively neutral and stable. Later, sulfates became more common, pointing to water that was increasingly acidic and transient, a sign that the climate was shifting toward the cold, dry conditions we see today. It is a reminder that even worlds without cities, forests, or oceans can still experience profound environmental change. Comparing early Mars to a young Earth is an exercise in both similarity and contrast. About 4 billion years ago, Earth was also a volatile, restless world with frequent impacts and active volcanism. Yet Earth had an advantage. It was larger, closer to the Sun, and able to hold onto a thick atmosphere. This allowed its surface water to persist, forming the seas that would eventually cradle life. Mars, with its smaller size and weaker gravity, could not keep its atmosphere for as long. It may have had a similar start. Lakes, rivers, perhaps even a shallow ocean in the northern lowlands. But it was living on borrowed time. That limited window, however, might still have been enough. On Earth, life's earliest traces appear in rocks about 3.5 billion years old, and some evidence hints at even earlier origins. If Mars had liquid water for hundreds of millions of years, it is not unreasonable to wonder if life could have emerged there too, even if only as microbes. The chemistry was certainly possible. Water is an exceptional solvent, capable of dissolving and transporting nutrients, and with sunlight, volcanic heat, and minerals in the mix, the ingredients for life were present. The big unknown is how long these conditions lasted. Some scientists think Mars's rivers and lakes were seasonal or episodic, appearing during warmer intervals caused by volcanic eruptions or orbital shifts. Others argue that early Mars had a much thicker atmosphere and could have supported long-lived bodies of water. In either case, the traces left behind suggest a world that went through wetter and drier phases, gradually tipping toward dryness. It is also worth considering that water on Mars may not have disappeared entirely when the surface dried out. Much of it could have gone underground, locked in ice, or trapped as briny liquids beneath layers of soil. In some polar regions, radar data from orbiters suggests the presence of subglacial lakes, though their existence is still debated. If they do exist, they could be modern-day echoes of a much wetter past. The most evocative part of this story is how these rivers, deltas and minerals remain visible after billions of years. On Earth, our landscapes are constantly recycled. Rivers shift, mountains erode, tectonic plates destroy and create crust. Mars, with its geological stillness, preserves these features as though they were frozen in time. You can trace the course of an ancient river from its source to its mouth, seeing every bend and branch as clearly as if the water had dried up only yesterday. The sight is both beautiful and haunting. Beautiful because the patterns are universal. The way water shapes land does not depend on the planet. Haunting because they are empty, the rivers long gone, the lakes dry, the ocean floor cracked and dusty. They remind us that worlds change, sometimes dramatically, and that the conditions for life can be fleeting. If early Mars truly was a world of rivers, it must have been a striking place to stand. You might have seen water shimmering under a pinkish sky, mountains casting long shadows over valleys, and clouds drifting slowly overhead. You could have followed a riverbank and watched as it spilled into a wide, calm lake, its edges marked by greenish minerals just beneath the surface. Whether any living thing stood there to witness it is a question we have yet to answer. What we do know is that these rivers, long gone though they are, still speak. They speak through the shapes they carved, the sediments they left, and the minerals they formed. They speak of a Mars that was once alive in its own way, a world of movement, cycles, and possibility. In listening to them, we listen not just to Mars's history, but to the shared language of planets shaped by water. In the far north of Mars lies a vast, low-lying expanse known as the Northern Plains. From orbit, this region looks strikingly different from the heavily cratered highlands to the south. It is smoother, flatter, and stretches for thousands of kilometers, as if some great force once swept across it and left behind an even surface. For decades, planetary scientists have wondered if that force might have been water, not trickling streams or shallow lakes, but an entire ocean. The idea of a Martian ocean is not new. In the 1980s, maps of Mars elevation, compiled from spacecraft data, revealed something intriguing. A huge portion of the northern hemisphere sits several kilometers lower than the southern highlands. This difference in height forms a natural basin, one that could, in theory, have held a body of water covering as much as 1/3 of the planet's surface. On Earth, such a basin would almost certainly be filled with an ocean, and the similarities were too compelling to ignore. Further evidence came in the form of what looked like ancient shorelines, long winding ridges and terraces that trace curves across the landscape. Some stretch for thousands of kilometers, wrapping around the edge of the northern plains. They resemble the raised beaches or wave-cut cliffs found along coastlines on Earth, where water once lapped and retreated over centuries. While erosion on Mars is slow, these features have endured for billions of years, their shapes hinting at a time when tides, or something like them, may have shaped the land. The story these shorelines suggest is staggering. Imagine an ocean filling the northern lowlands, perhaps hundreds of meters deep in some places, connected to rivers and lakes that drained from the southern highlands. Volcanic heat, impacts, and a thicker atmosphere could have kept this water liquid for millions of years. The surface might have been dotted with icebergs in winter, with waves and spray under the pale pink sky. It is a vision both alien and oddly familiar, a reminder that oceans are not unique to Earth. But if such an ocean existed, it is long gone now. To understand why, you have to follow the trail of Mars' atmosphere. In its youth, Mars likely had a much denser blanket of air, thick enough to trap heat and maintain surface pressure. That pressure is vital. Without it, liquid water evaporates or freezes almost instantly. As Mars cooled and its magnetic field faded, the atmosphere began to escape into space. The solar wind, a constant stream of charged particles from the sun, stripped it away, molecule by molecule over hundreds of millions of years. With each lost molecule, the surface conditions became harsher. Temperatures dropped, air pressure fell, and water was pushed toward two fates: freezing solid or disappearing as vapor. An ocean under such conditions would gradually shrink, retreating into isolated lakes and eventually into ice. Some of that ice became locked in the polar caps, where it remains today. Some seeped underground, frozen into the soil, and some may have escaped entirely, joining the atmosphere's slow drift into space. NASA's MAVEN spacecraft, which has been orbiting Mars since 2014, has confirmed that atmospheric loss is still happening. Though the rate today is tiny, over geological time it has been enough to transform the planet. When scientists calculate how much water Mars has lost, they find that it could indeed have once supported a northern ocean. The chemical signatures in the atmosphere, particularly the ratio of heavier to lighter hydrogen isotopes, match the story of a world that has slowly bled away its seas. There are still debates, of course. Some scientists argue that the supposed shorelines might be something else entirely, the product of lava flows or tectonic uplift. Others point out that if the ocean existed, it may not have been a single stable body of water. Instead, it could have formed and vanished in cycles, appearing during warmer periods triggered by volcanic activity or changes in the planet's tilt, then freezing or evaporating as conditions worsened. Mars, in this view, may have had not one ocean but several temporary seas spread across millions of years. Even with the uncertainties, the possibility of an ocean changes how we think about Mars' history. An ocean would have been a vast reservoir for chemical reactions, a place where nutrients from rivers mixed and settled. On Earth, shallow seas are often cradles of life, rich in energy and resources. If Mars ever hosted living organisms, a northern ocean would have been an ideal habitat, at least until the climate turned against them. What makes the idea haunting is not just that the ocean is gone, but how complete its disappearance has been. Stand on the edge of the northern plains today, and there is no glint of water, no sound of waves, only silence and wind over a frozen desert. The beach-like ridges are there, but the sea they marked has been erased so thoroughly it is almost a ghost. You can trace the imagined line where the water once met the land and picture waves breaking, but the sound never comes. On Earth, even ancient seas leave behind shells, coral and marine sediments. On Mars, the search for such remnants is harder. Rovers and orbiters are looking for mineral traces that could have formed in long-standing salty water, for patterns in rock that suggest wave action, and for chemical signs of past habitability. Each clue adds to the picture, but the ocean remains, for now, a vision drawn in lines and elevations, a memory preserved in the shape of the land. It is sobering to think that billions of years ago Mars might have been a blue and red world, its northern hemisphere glittering with open water. Now it is entirely red, its seas lost to space and ice. The transformation is a reminder of how fragile planetary conditions can be, and how quickly, in cosmic terms, a world can change. If you could stand there in the age of the ocean, you might have felt a thin breeze carrying the scent of minerals from faraway rivers. You could have watched the sun sink toward the horizon, its light scattering through a sky just dense enough to hold warmth. But the night would have been cold, the stars sharp above the ice along the shore, and the ocean, for all its beauty, would already have been living on borrowed time. Now all that remains is the basin, the possibility, and the haunting thought of waves that will never crash again. The shoreline waits in silence, tracing the memory of a sea that once was, under a sky that can no longer hold it. If you could visit Mars in its earliest days, the first thing you might notice is how different the air would feel, or rather, how much more of it there would be. Billions of years ago, Mars likely had an atmosphere thick enough to wrap the planet in a blanket of warmth, keeping water liquid on the surface and softening the sun's harsh rays. Over time, however, that blanket grew threadbare. Today, the Martian sky is held aloft by an atmosphere less than 1% the thickness of Earth's. It is a ghost of what it once was, a fragile veil of gases that can barely cling to the planet. The question of where all that air went has fascinated scientists for decades. The answer, as it turns out, begins deep inside Mars itself. Like Earth, early Mars probably had a molten, churning core made of metal. The movement of that molten iron and nickel would have generated a magnetic field, an invisible force that surrounds a planet and shields it from the constant stream of charged particles coming from the sun, known as the solar wind. On Earth, our magnetic field is strong enough to deflect most of this solar wind, diverting it around the planet and preventing it from stripping away our atmosphere. Mars, however, had a different fate. Because of its smaller size, Mars cooled more quickly than Earth. Its molten core solidified, the dynamo that powered the magnetic field slowed, and eventually the shield collapsed. Without that protection, the solar wind could sweep directly against the upper atmosphere, knocking atoms into space like leaves caught in a steady gale. This stripping process happened over millions of years, but its effects were profound. The lighter gases escaped first. Hydrogen and helium vanished easily into space. Then, molecule by molecule, carbon dioxide and water vapour were carried away. Without a thick atmosphere to trap heat, surface temperatures plummeted. Water that had once flowed freely froze into ice, or sublimated directly into vapour, leaving behind dry riverbeds and empty lake basins. The MAVEN spacecraft, which has been studying Mars since 2014, has given us a clearer picture of this slow unravelling. It has measured how solar storms accelerate atmospheric loss even today. Though the current rate is minuscule, the accumulated effect over billions of years is enough to explain much of the missing air. Mars's sky, once blue and dense, became thin and dusty, with barely enough pressure to whisper against the rocks. Standing under that sky today would be an eerie experience. The light would feel strange, dimmer than on Earth, yet still sharp. The sun would appear about 2/3 the size it does from Earth, its brightness filtered through a haze of reddish dust. The air would not carry the scents we're used to, because it is too thin to carry much at all. If you tried to breathe it without a suit, it would not be the cold that killed you first, but the lack of pressure. Your lungs simply could not draw in enough oxygen to survive. The wind, too, would be deceptive. At its strongest, it might reach speeds of 100 kilometers per hour, but with so little air to push against you, it would feel like a gentle breeze. It is a curious paradox. A planet capable of global dust storms that can shroud its entire surface, yet whose air is so tenuous you could barely feel it on your skin. The thinness of the atmosphere also changes the way the sky looks. By day, the horizon is a muted rusty tan, blending into the salmon-coloured ground. Near the sun, the dust scatters light in such a way that the sky can appear butterscotch, or even faintly yellow. At sunset, the effect reverses. The dust scatters red light away and lets blue light pass through, giving Mars the rare trick of having blue sunsets. They are brief and muted compared to the fiery displays on Earth, but their soft glow across the quiet landscape is one of the planet's most haunting sights. Without much atmosphere, heat does not linger after sunset. The days can be chilly even under full sunlight, but the nights are bitterly cold. Temperatures can drop by dozens of degrees in just a few hours. It is an environment where warmth has nothing to hold on to, radiating away into space almost as quickly as it arrives. The loss of atmosphere did more than change the climate, it changed the planet's potential. With thicker air, early Mars might have been a place where life could survive, shielded from radiation and kept warm enough for liquid water to remain stable. As the air thinned, that window closed. Radiation from the sun and deep space now reaches the surface far more easily, bombarding it with levels that would be hazardous for most known life. Any life that might have existed would have been forced to adapt underground or disappear altogether. And yet, even in its diminished state, Mars's sky still holds beauty. The dust gives it texture, painting subtle gradients at dawn and dusk. Wispy clouds made of ice crystals or carbon dioxide sometimes drift high above, catching the sunlight in pastel shades. In the thin air, these clouds move slowly, casting faint shadows on the ground below. There is a stillness to it, a silence not broken by rustling leaves or the distant hum of insects. The sky feels vast, unbroken, and strangely intimate all at once. To stand under that sky is to be reminded of time on a scale far beyond human lifetimes. Every atom of the lost atmosphere tells a story of billions of years of change, of a planet that could not hold on to what it once had. It is a lesson written not in books, but in the colour of the horizon, in the sharpness of the stars at night, in the gentle hiss of a wind too light to carry your voice. And perhaps that is the most striking thing. The thin Martian sky is not just empty space above your head, but the visible remnant of a long, slow transformation. It is the ghost of a climate that might once have been comfortable, the reminder of a shield that failed, and the fragile ceiling over a world still whispering its history into the void. If there is one thing Mars has in abundance, it is dust. Not the kind of dust you might find under a sofa, but an endless planet-wide layer of fine, iron-rich powder that seems to cling to everything it touches. This dust is what gives Mars its distinctive reddish hue, a colour so tied to the planet that we now call it the red planet without a second thought. But that red is not the colour of the rocks themselves. It is the thin coat of oxidised iron that covers nearly every exposed surface. The story of this dust begins with the rocks of Mars' crust. Over billions of years, wind and temperature changes have ground the surface down into particles smaller than a grain of talcum powder. The chemical composition of these rocks includes iron, which when exposed to trace amounts of oxygen in the thin atmosphere slowly rusts. The result is iron oxide, the same compound that gives Earth's deserts their red tones and a forgotten bicycle its orange patina. On Mars, there has been more than enough time for oxidation to work its way into nearly every grain of soil. Because the particles are so fine, they behave almost like smoke in the air, able to remain suspended for long periods. Even a modest gust of wind can lift them from the ground and carry them for kilometres. Over the ages, this process has given Mars a thin but persistent haze, especially in the lower atmosphere. From the surface, it softens the light, creating the planet's characteristic butterscotch skies. From orbit, it mutes the colours, painting everything in shades of rust and ochre, but the dust is not evenly distributed. Local conditions can create towering dust devils, some stretching more than a kilometre into the sky, swirling across the plains and leaving dark tracks in their wake. These whirlwinds are powered by sunlight heating the surface, causing air to rise and spin in the thin atmosphere. Despite their size, they are gentle by Earth standards. You could stand inside one without being knocked over, but they are incredibly efficient at lifting dust high into the air. Beyond the local whirlwinds are the real giants of Martian weather, global dust storms. Every few years, under the right conditions, dust lifted from one region can be carried around the entire planet. As more dust rises, it traps heat in the atmosphere, which changes wind patterns and lifts even more dust in a kind of runaway cycle. Within weeks, the storm can engulf Mars entirely, turning it into a uniform sphere of pale orange when viewed from space. These storms can last for months, and while they may not bring the drama of howling winds and stinging grit that Hollywood likes to imagine, they are no less formidable in their own way. The winds are fast, but carry little force because the air is so thin. Instead, the danger comes from the dust itself, which blocks sunlight from reaching the surface. For solar-powered spacecraft, that loss of light can be catastrophic. In 2018, a planet-wide dust storm ended the mission of NASA's Opportunity rover after nearly 15 years of exploration. Its solar panels were starved of energy, and without power to keep its systems warm, the cold claimed it. Dust also shapes the climate of Mars on longer timescales. When airborne, it absorbs and scatters sunlight, warming the atmosphere while cooling the ground beneath. This can change temperature gradients across the planet, affecting wind patterns and potentially influencing the behaviour of polar ice. Some scientists think that dust has helped to keep Mars in its current cold, dry state by altering the way heat moves between the surface and the air. The influence of dust is not just a matter of climate, it is a constant challenge for exploration. Every spacecraft that lands on Mars must contend with it. The fine particles can work their way into joints, gears, and hinges, wearing them down over time. They cling stubbornly to surfaces, coating camera lenses and solar panels alike. Engineers design rovers and landers with dust in mind, sometimes including mechanisms to shake or brush it away, but there is no perfect solution. The longer a mission lasts, the more dust accumulates. Even human explorers of the future will have to think carefully about dust. On Earth, lunar dust brought back by Apollo astronauts proved to be surprisingly sharp and clingy, and Martian dust is likely to be similar. It may pose health risks if inhaled, and its electrostatic nature means it could stick to spacesuits and be carried into living quarters. The same iron oxide that makes Mars so visually striking could become a stubborn and dangerous nuisance in daily operations. And yet, for all its challenges, the dust is also part of what makes Mars so visually compelling. It smooths sharp edges, softens colours, and creates subtle, shifting patterns across the surface. In some regions, windblown dunes ripple like frozen waves, their dark basaltic sand standing in stark contrast to the pale dust that settles between them. In others, dust collects in the sheltered leeward sides of the rocks, drawing faint outlines like shadows cast by the wind itself. The dust is also an archive of Mars history. Trapped within it are tiny fragments of rock from across the planet, mixed and remixed by winds over eons. By studying its composition, scientists can learn about the geology of places far from their landing sites, as though Mars has spent billions of years passing around samples for inspection. It is possible that the dust even holds chemical clues to the planet's past habitability. If microbial life ever existed on Mars, traces of its activity might have been preserved in mineral grains or locked in fine layers of sediment. Though the odds of such a discovery are uncertain, the dust offers a tantalizing target for future analysis, a record of the planet's surface processes and perhaps, just maybe, of its biological history. From the soft haze it creates in the sky to the massive storms that can blanket a world, Martian dust is a constant presence. It is both a storyteller and a troublemaker, preserving the past while complicating the future. Every rover wheel that leaves a track in it, every gust of wind that stirs it into the air, continues a cycle that has been running since the first rocks on Mars began to crumble. And perhaps that is the essence of the dust planet. It is a world where even the smallest particle matters, where the colour of the sky and the fate of a mission can hinge on something so fine you could hold millions of grains in the palm of your hand. On Mars, dust is not just part of the landscape. It is the landscape, endlessly shifting and endlessly patient, waiting for the next wind to lift it once more. On Earth, the tallest mountain is Mount Everest, its peak rising just over 8.5 kilometers above sea level. Impressive, certainly, but on Mars, Everest would look almost modest. There, in the Western Hemisphere, towers Olympus Mons, a volcano so large it defies easy comparison. From base to summit, it stands about 22 kilometers high, nearly 3 times the height of Everest. Its base is so wide it could cover the entire state of Arizona or the country of France, and if you were standing on one side, the curvature of Mars would hide the other. Olympus Mons is what geologists call a shield volcano, built up over millions of years by repeated lava flows that spread outward in gentle slopes rather than steep cliffs. The lava on Mars is relatively fluid, allowing it to travel great distances before cooling and solidifying. With no tectonic plates to shift the crust beneath it, the volcano stayed fixed over its heat source, erupting in the same spot again and again. On Earth, moving plates carry volcanic hotspots along, creating chains of volcanoes like Hawaii. On Mars, the stationary crust allowed Olympus Mons to keep growing taller and wider without interruption, eventually becoming the largest volcano in the solar system. It is not alone in its grandeur. To the east of Olympus Mons lies the Tharsis region, a vast volcanic plateau dotted with other colossal peaks, Ascraeus Mons, Pavonis Mons and Arsia Mons. Each of these volcanoes would be a wonder in its own right if they stood on Earth, but here they are almost overshadowed by their gigantic neighbour. Together, they rise from the same uplifted region, a bulge in the crust so massive that it may have influenced the planet's tilt, and even contributed to the formation of the enormous canyon system known as Valles Marineris. These volcanoes tell us a great deal about Mars' geological past. Their sheer size and number indicate that the planet was once far more active than it is today. Volcanism requires heat from within, and in Mars' early history that heat was abundant. Molten rock pushed upward through weak points in the crust, pouring across the surface in flows that could stretch for hundreds of kilometers. Some eruptions may have lasted for weeks or months, releasing vast amounts of gas and ash into the atmosphere. If there was water present on the surface or in the ground, these eruptions could have triggered floods of melted ice, carving channels and reshaping the landscape in dramatic bursts. But for all their power, the great volcanoes of Mars are now silent. The last known volcanic activity on the planet may have been as recent as a few million years ago, practically yesterday in geological terms. But Olympus Mons and its siblings have not erupted in recorded history. Without tectonic movement and with much of its internal heat dissipated, Mars's mantle has grown still, unable to feed the colossal structures it once built. The stillness is striking. Imagine standing near the base of Olympus Mons, looking up at a slope so gentle that, from your vantage point, it might seem more like a hill than a mountain. Yet that slope stretches for hundreds of kilometers before it finally reaches the summit. Climbing it would be a strange experience. The low gravity would help, but the scale would be disorienting. You could walk for days and feel as though you were barely making progress, the horizon forever retreating. The caldera at the summit, the collapsed crater left after eruptions emptied the magma chamber below, is large enough to swallow entire cities. It is ringed by cliffs and fractured by ancient faults, a reminder of the forces that once surged beneath. Now it is silent, dust settling in thin layers over rock that has not felt the heat of magma in ages. Elsewhere on Mars, smaller volcanic features add to the planet's complex story. There are lava plains stretching across thousands of square kilometers, dotted with shield volcanoes that never reach the monstrous scale of Olympus Mons. There are volcanic cones formed from explosive eruptions that hurled ash and cinders into the air, creating steep-sided mounds. Some regions show signs of fissure eruptions, where lava poured from long cracks in the ground rather than central vents, leaving behind dark, sinuous flows visible even from orbit. The evidence of volcanism on Mars is more than just a record of past fire. It also holds clues about the planet's internal structure, its cooling history, and even its potential for past habitability. Volcanic activity releases gases into the atmosphere, including water vapour and carbon dioxide, which can warm a planet and support a thicker atmosphere. On early Mars, eruptions may have played a role in maintaining conditions that allowed liquid water to persist on the surface. The heat from volcanic regions could also have created pockets of warmth beneath the ice, potentially offering refuges for life. Today the volcanoes stand as monuments to that more dynamic time. They are so large and stable that, unlike mountains on Earth, they will not crumble quickly under erosion. The thin atmosphere, lack of rainfall and slow pace of weathering mean that Olympus Mons will likely look much the same millions of years from now as it does today. It is a mountain that has outlived the forces that made it, a relic of a planet that has largely gone still. There is a certain poignancy in their silence. On Earth, volcanoes are reminders that the planet is alive beneath our feet, constantly reshaping itself. On Mars, they are reminders of a world that once breathed fire and now rests in a long, cold slumber. The mountains that touch the stars are frozen in time, their vast slopes bathed in the soft light of a distant sun, their summits rising into a thin sky where only dust moves freely. If you were to stand there, you might feel a kind of awe that is difficult to put into words. Not the awe of imminent danger, but the awe of immense scale and deep history. Every rock underfoot would be a piece of the planet's fiery past, every horizon a gentle curve of a mountain unlike any on Earth. It is a place where time moves differently, where millions of years pass in quiet, and where the echoes of ancient eruptions still shape the land, even in the silence that follows. If the Grand Canyon on Earth impresses you with its sheer scale, Valles Marineris on Mars would leave you speechless. Stretching for over 4,000 kilometers, it is nearly 10 times longer than the Grand Canyon. In places, it is more than 200 kilometers wide and plunges as deep as 7 kilometers. If it were on Earth, it would run almost the entire width of the United States, from New York to California, swallowing whole mountain ranges along the way. Seen from orbit, it is a scar so vast that it dominates the face of the planet. The name comes from NASA's Mariner 9 spacecraft, which first revealed its staggering size in the early 1970s. Until then, nobody expected such a feature on Mars. The canyon's proportions defy easy comparison, not just because of its length and depth, but because of its complexity. Valles Marineris is not one continuous trench, but a network of interconnected chasms, each with its own cliffs, slopes, landslides, and layered walls. From above, it resembles a series of parallel cracks that have been widened and deepened over unimaginable spans of time. How such a feature formed remains one of the great geological debates in planetary science. On Earth, canyons are typically carved by rivers, glaciers, or a combination of both. But Mars does not seem to have had enough flowing water for long enough to cut something of this scale. Instead, most scientists believe Valles Marineris began as a giant tectonic fracture. In the planet's distant past, the immense volcanic activity of the Tharsis region to the west may have uplifted the crust, stretching it until it cracked. Once those fractures formed, they could have been widened by landslides, the collapse of underground caverns, and even bursts of water or lava that eroded the walls. There is evidence that water did play a role, at least in parts of the canyon. Some regions contain channels and sediment deposits that suggest ancient floods or lakes. These bodies of water, if they existed, would have been temporary, appearing during warmer periods or after volcanic heating melted underground ice. Over time, they would have frozen or evaporated, leaving behind only the layered rock and mineral traces we see today. The canyon's walls are a geological archive, revealing layers upon layers of rock laid down over billions of years. Each stratum tells a story of a different era: volcanic ash from distant eruptions, sediments from ancient rivers, and deposits shaped by wind over long dry periods. Landslides have exposed these layers in spectacular cross-sections, creating cliffs that could be taller than Mount Everest. From the bottom, the view upward would be dizzying. Sheer walls stretching kilometers above, their colors shifting from deep reds to pale yellows in the thin sunlight. The scale of Valles Marineris is difficult to fully appreciate without being there. Imagine drifting along in a spacecraft at low altitude, following the canyon floor for days as its walls rise and fall around you. In some stretches, the canyon widens into vast basins, where side canyons branch away like tributaries. In others, it narrows to tight corridors where the walls crowd close, casting long shadows even at midday. In the thin Martian air, light scatters differently, and the shadows would have a softness to them, their edges blurred by the ever-present dust. From the ground, the canyon would feel like its own world within a world. The air pressure would be slightly higher at the bottom, and temperatures might be a little warmer, offering a rare bit of shelter from the planet's harsh climate. The wind would move differently here, funneled by the walls into long, slow currents that could carry dust for great distances without ever escaping to the plains above. In certain parts of the canyon, you might find the remnants of massive landslides. Piles of rock the size of cities, frozen mid-tumble in the low gravity. Some of these slides are so large that they rival the biggest known on Earth, a testament to how gravity and terrain interact differently on Mars. The debris spreads out in patterns that look almost fluid, as if the rock had flowed like thick mud before settling into place. Looking upward, the sky would be a narrow strip, sometimes little more than a ribbon of pale light between the cliffs. At dawn, sunlight would creep down the walls in stages, painting the rock in gold before finally touching the canyon floor. At sunset, the reverse would happen, the light climbing back up the walls until only the peaks remained lit, glowing briefly before fading into the deep rust of twilight. The scale also invites thoughts of exploration. A rover travelling the floor of Valles Marineris would be dwarfed by its surroundings, the cliffs looming like the walls of an alien cathedral. For human explorers, the canyon might offer both challenges and opportunities. Its shelter from wind and radiation could make it an attractive base, while its exposed rock layers would be a treasure trove for geologists searching for clues about Mars' history. But getting in and out would be no small feat. The descent alone would be a journey of hours or even days, depending on the route. Some scientists have even speculated that caves might exist within the canyon walls, carved by ancient lava flows or by water erosion. Such caves, if they exist, could offer some of the most protected environments on the planet, shielded from radiation and temperature extremes. They might also be the best places to look for preserved signs of past life, if Mars ever hosted it. And yet, for all its geological importance, Valles Marineris is just as captivating for its raw beauty. From space, its length is almost absurd, a reminder that planetary forces operate on scales far beyond our daily experience. On the ground, its cliffs and slopes would offer endless variations in light and shadow, colour and texture. It is a place where the imagination can wander almost as freely as the dust devils that roam its floor. The Grand Canyon on Earth can make you feel small, but Valles Marineris could make you feel microscopic. To drift through its depths, whether in a spacecraft, a rover, or just in the mind's eye, is to witness a planet's history written on a scale so vast it feels almost impossible. It is a scar, a rift, a monument, and perhaps even a sanctuary, carved into the red rock by forces we are only beginning to understand. At the top and bottom of Mars lie two gleaming caps of ice and dust, the planet's frozen crowns. From orbit they stand out sharply against the rust-red terrain, bright spirals and swirls that look almost delicate, as if they were painted onto the surface with a steady hand. In reality, they are massive deposits of frozen water and carbon dioxide, stacked in layers that record the planet's climate over millions of years. The North Polar Cap, known as Planum Boreum, is the larger of the two. In the height of northern summer, it is made mostly of water ice, its surface etched with graceful curving troughs carved by winds. The South Polar Cap, Planum Australe, is smaller but thicker, and its base may contain a layer of carbon dioxide ice that has persisted for millennia. Both caps sit atop layered deposits, like the rings of a tree, built from alternating seasons of snowfall, frost and dust. These layers are a kind of natural archive, preserving a record of Mars's shifting tilt and changing climate. Unlike Earth's poles, which are cloaked in thick ice year-round, Mars' poles undergo dramatic seasonal transformations. This is because much of the ice you see in pictures is not water ice at all, but dry ice. Frozen carbon dioxide. Each Martian year, as winter grips one pole, temperatures plunge so low that carbon dioxide from the atmosphere freezes directly onto the surface, adding a seasonal layer up to a metre thick. At the same time, the opposite pole is in summer, and its dry ice layer sublimates, turning straight from solid to gas, to rejoin the atmosphere. This annual breathing in and out of carbon dioxide is so significant that it changes the pressure of the planet's atmosphere. In winter, when carbon dioxide freezes at one pole, the total atmospheric pressure drops. In summer, as that frozen carbon dioxide returns to the air, the pressure rises again. The poles act like giant valves, cycling a large portion of the atmosphere between solid and gas every year. The process is most striking to watch during the transition between seasons. As sunlight creeps back across a winter pole, the dry ice begins to sublimate from the bottom, trapping gas beneath the remaining ice. Eventually the pressure builds enough to crack the surface, releasing sudden jets of gas that carry dust and sand with them. From above, these eruptions leave dark, fan-shaped stains on the ice, marking the direction of the prevailing winds. It is a strange and beautiful phenomenon, unique to a world where the atmosphere itself regularly freezes solid. Beneath the seasonal layers of dry ice, the permanent water ice of the poles holds an enormous reservoir. If all the water ice from Mars' poles were melted, it could cover the planet in a global ocean over 10 meters deep. This water is a key target for future exploration, not just because of its scientific value, but because it could sustain human missions. Ice could be mined for drinking water, broken down into oxygen for breathing, and used to make rocket fuel. The poles also reveal patterns in Mars' longer-term climate history. The planet's axial tilt, or obliquity, changes dramatically over cycles lasting hundreds of thousands to millions of years. At times, Mars tilts more steeply, causing the poles to receive more sunlight and warm enough to release large amounts of ice into the atmosphere. At other times, the tilt lessens, and the poles grow colder, locking more water into their icy layers. The stratified deposits at both poles capture these shifts in fine detail, each layer a frozen page from Mars' climate record. From the ground, the poles would be unlike any other place on Mars. The horizon would be a smooth sweep of white, broken by streaks of wind-blown dust. The air would be even colder than the rest of the planet, and in the thin atmosphere frost would cling to every surface. Even the dust here can be tinged with frost, giving the landscape a muted sparkle under the pale sun. The silence would be absolute, broken only by the faint hiss of wind over ice. During winter, the poles are cloaked in darkness for months at a time, and temperatures can plunge below -100 degrees Celsius. In summer, the sun never sets, instead circling the horizon and casting long, shifting shadows across the ice. The constant light reveals subtle textures, ripples formed by wind, pits carved by sublimating ice, and the spiral troughs that wind deep into the polar caps like frozen mazes. The beauty of the poles lies not just in their stark contrasts, but in their fragility. The frost that forms across the polar deserts each winter can be only a few millimeters thick, yet it transforms the landscape completely, turning rust-coloured dunes into shimmering white hills. As the seasons change, the frost retreats, revealing the red and brown beneath once more. It is a transformation repeated year after year, as reliable as the dance of the planets around the sun. Looking down from orbit, you can trace the delicate spirals and curves of the polar caps and imagine the winds that shaped them. You can see the way the ice glows in the sunlight, its brightness unsoftened by haze or cloud. It is a beauty untouched by life, shaped only by the interaction of light, air, and frozen ground. For all their remoteness, the poles are vital to understanding Mars. They are not just static reservoirs of ice, but active participants in the planet's climate, controlling the flow of carbon dioxide and recording the rhythms of past ages. They may even hold clues about the history of water on Mars, and by extension, its potential to have supported life. Standing there, beneath a pale sun circling endlessly above, you would feel the weight of time in every layer beneath your feet. Each one is a chapter in a story that stretches back millions of years, written in ice and dust, waiting for someone to read it. And all around, the frozen desert would shimmer softly, as if the planet itself were exhaling frost into the thin, still air. High above Mars, two small moons circle through the thin, dusty sky, Phobos and Deimos. They are nothing like our own large, bright moon. These companions are irregular, lumpy, and dark, more like misshapen asteroids than miniature planets. In fact, if you were expecting a majestic lunar disk rising over the Martian horizon, you might be surprised to see instead a potato-shaped rock drifting silently overhead. Phobos, the larger of the two, is still quite small by moon standards. It is only about 22 kilometers across at its widest point, a size that would barely register as a dot if placed next to our moon. Deimos is even smaller, roughly 12 kilometers across, and looks more like a giant space boulder than anything else. Their surfaces are pocked with craters, their shapes irregular, and their colours muted to a dull grey-brown. They lack the spherical symmetry of larger worlds, their low gravity unable to pull them into perfect roundness. Because they are so small, both moons have an uncanny quality when seen from the Martian surface. Deimos, the more distant of the two, rises and sets much like our moon does, though it appears only as a bright star-like point to the naked eye. Phobos, however, orbits so close to Mars that it races across the sky in just over 7 hours. It rises in the west, sets in the east, and can be seen crossing the heavens several times in a single Martian day. Standing on Mars, you could watch Phobos rise in the late afternoon, and then see it set again before midnight. Where these moons came from is still a matter of debate. One theory suggests they are captured asteroids, pulled in from the nearby asteroid belt or perhaps even from farther out. Their shapes and dark surfaces resemble a class of asteroids called carbonaceous chondrites, which supports this idea. However, capturing an asteroid into a stable orbit without it crashing into the planet or slingshotting back into space is tricky. Mars would have needed the right combination of gravity, timing, and perhaps a thicker atmosphere in the past to slow the objects down. Another theory is that Phobos and Deimos formed much closer to Mars, born from debris left behind after a massive impact. In this scenario, a large asteroid struck Mars billions of years ago, ejecting vast amounts of rock and dust into orbit. Over time, that material clumped together into the two small moons we see today. This explanation neatly accounts for their current orbits, but it leaves open the question of why their composition appears so similar to distant asteroids. Whatever their origins, the two moons lead very different orbital lives, Deimos, the smaller and more distant, is slowly drifting away from Mars. In millions of years it may wander off entirely, slipping into a solar orbit and leaving Mars behind. Phobos, on the other hand, is on a doomed inward spiral. It orbits only about 6,000 kilometers above the Martian surface, so close that it is actually below the planet's synchronous orbit, where a satellite would hover over the same spot. As a result, Mars' gravity is gradually pulling Phobos closer. Each century, Phobos drops about 2 meters toward the planet. That may not sound like much, but given enough time, the outcome is inevitable. In roughly 30 to 50 million years, Phobos will either crash into Mars or break apart under the stress of tidal forces, forming a temporary ring around the planet. If the latter happens, Mars would briefly become a ringed world, its new adornment slowly spreading and thinning before the particles either spiral down to the surface or drift away. It would be a dramatic, if fleeting, transformation. Phobos already bears signs of its eventual fate. Its surface is covered in long grooves and fractures, some of which may be the result of repeated impacts, but others could be stress cracks caused by the relentless pull of Mars' gravity. These fractures hint that the Moon's internal structure might be weak, making it more likely to break apart before it ever reaches the surface. For future explorers on Mars, the moons could be both useful and inspiring. Phobos, with its low gravity, would make an excellent platform for observation and communication, acting almost like a space station in constant orbit. Deimos, though farther away, offers an even gentler gravity well, and could serve as a staging point for missions deeper into the solar system. Both moons would provide unparalleled views of Mars itself, a planet hanging in the black sky, its deserts, canyons and volcanoes sprawling beneath the thin veil of atmosphere. From the Martian surface, Phobos would be the more dramatic sight. During the day, it can cast a shadow across the landscape as it passes in front of the sun, creating partial eclipses that sweep rapidly across the ground. These eclipses last only about 30 seconds, a brief dimming of the already pale sunlight, but they are spectacular in their speed. Deimos's eclipses, by contrast, are subtle, little more than a faint wink in the sky. There's also a quiet beauty to the moons when seen at night. Deimos glides slowly, a small bright bead against the stars, while Phobos hurries past, crossing from horizon to horizon in a matter of hours. In the stillness of the Martian evening, they are constant companions, reminders that even a solitary planet in a vast emptiness is rarely truly alone. Their orbits, their shapes, and their fates are part of Mars' ongoing story. Phobos is the restless one, forever falling inward, destined to shatter or burn. Deimos is the wanderer, inching outward toward freedom. Between them, they frame the planet's skies in miniature, carrying the marks of their origins and the certainty of their endings. For now, though, they remain in their ancient dance. 2 tiny moons circling a quiet planet, keeping watch over a world that has changed so much since they first took their places in its orbit. And for anyone standing on Mars looking up into the thin, dusty sky, their presence would be a reminder that even the smallest companions can shape the way we see a world. When people imagine Mars, the colour that comes to mind first is red, deep, rusty and unmistakable. It is such a defining feature that the planet is known as the Red Planet in almost every language. But that signature colour is not the natural hue of every rock and hill. It is the work of a fine, powdery coating that blankets almost the entire planet, dust rich in iron oxide. The chemistry behind it is simple enough. The rocks of Mars contain iron, just as many rocks on Earth do. Over billions of years, those rocks have been broken down into tiny grains by wind, impacts, and temperature changes. In the presence of trace amounts of oxygen, supplied by the thin atmosphere, the iron oxidizes, forming the reddish compounds we call rust. This process has been happening for so long that the surface of Mars is covered in a layer of iron-rich dust just a few microns thick, enough to give the entire planet its burnt orange glow. From space, the effect is striking. Against the blackness of the cosmos, Mars gleams like a glowing ember. But up close, the colours are far more complex. The rusty tones dominate, but they are not uniform. In some regions, the dust has been swept away by wind, revealing darker volcanic rock beneath. These exposed areas can appear charcoal grey or even black, their basaltic composition absorbing more sunlight. Other places are paler, their dust mixed with lighter minerals that soften the red into peach or tan. Minerals also bring unexpected colours to the Martian palette. Certain salts and clays can appear in shades of greenish-grey or bluish tones, especially when viewed under the bright midday sun. Sulfates, which form in the presence of water, can leave behind pale yellow or whitish deposits. In some craters, orbital images have revealed streaks of almost pure white, likely patches of exposed water ice or frost clinging to shaded slopes. Even the polar caps from a distance gleam brilliant white in winter, only to take on subtle pinkish hues as dust settles across them in summer. Volcanic regions add still more variety. The lava plains surrounding Olympus Mons and the Tharsis volcanoes often appear darker than their surroundings, the iron in their basalt not yet fully oxidized. Over time, wind will carry dust across these surfaces and coat them, but for now the contrast between the dark rock and the lighter dust is a reminder that Mars's surface is a patchwork of both ancient and relatively fresh landscapes. Seasonal changes also bring shifting shades. During the vast dust storms that can envelop the entire planet, the atmosphere takes on a soft orange glow, muting the shadows and flattening the contrast of the terrain. When the storms subside and the dust settles, the freshly coated landscape can look subtly different, the winds having rearranged the colours in broad, sweeping patterns. And then there is the sky. Most of the time, Mars's daylight sky is not blue like Earth's, but a warm butterscotch colour. This is because the fine dust suspended in the thin atmosphere scatters sunlight differently than the nitrogen and oxygen-rich air on Earth. The red dust scatters blue light away more efficiently, letting the warmer tones dominate. But at sunset, the effect reverses. The sky near the sun turns a soft blue while the rest of the horizon glows with deep oranges and reds. It is a gentle, almost pastel blue, lasting only a few minutes before fading into the darkness of space. Imagining Mars under a different sky is an interesting exercise. If the atmosphere were thicker and free of so much dust, Rayleigh scattering would dominate just as it does on Earth, and the daytime sky would likely be blue. The red tones of the ground would stand out more vividly, their contrast sharpened by the cool light above. In winter, a clearer sky might make the polar caps gleam even more brightly, their whiteness stark against the rust-red deserts. Under a thicker atmosphere, even the shadows would be different, softer, bluer, and less harsh in their transitions. One could also imagine Mars with a younger atmosphere, when it may have been warmer, wetter, and filled with clouds. In that ancient time, the colours might have been more muted, the dust less widespread. There may have been stretches of deep blue or green water, the surrounding rocks darker with the moisture. Clouds could have rolled across the sky in white or grey masses, filtering the sunlight and changing the tones of the land hour by hour. In such a world, the iconic red might not have been the dominant colour at all. Today, though, the planet's colours are shaped by its dryness. The dust does not wash away in rain, nor is it buried under snow for long. Instead, it moves slowly in the wind, settling in thin layers over everything it touches. Rovers leave dark tracks in the dust that fade over time as it drifts back into place. Craters appear lighter or darker, depending on whether their impacts excavated fresh material from beneath the surface or were later dusted over. There is a quiet artistry to it, a planet painted not in bold, fixed colours, but in soft layers that shift over centuries. The reds are the dominant brushstroke, but they are balanced by subtle greys, blacks, yellows, and whites. Each hue has a story, from the chemical transformation of iron to the seasonal dance of frost and dust. If you were standing on Mars, the colours would change with the time of day. In the morning, under the low sun, The land might glow a deep copper, shadows long and cool. At midday, the light would wash the surface into paler tones, and in the evening the red would deepen again as the sun dropped and the horizon turned gold. And then, just before nightfall, the sky would briefly bloom with blue, framing the last glint of the sun before the stars returned. Mars is called the Red Planet for good reason, but its colours are far richer than that single word suggests. It is a world painted in rust and shadow, in frost and stone, a canvas shaped by chemistry, climate and time, and in its shifting palette it holds a reminder that even the simplest hues can hide infinite variety, if only you take the time to look closely. Mars has always been a world we've known mostly through pictures, silent panoramas of rock and sky. For decades we could only imagine what it might sound like to stand on its surface. That changed in the year 2021, when NASA's Perseverance rover began recording with its microphones. For the first time, we could not just see Mars, we could listen to it. The first thing those microphones revealed is something that was already suspected. Mars is incredibly quiet. On Earth, even in the stillest moments, there is background sound. The distant rush of air, the hum of life, the murmur of water, insects, or machines. Mars has none of that. The soundscape is dominated by a deep, almost constant silence. When something does break it, the noise feels sharper, more isolated, as though the whole planet is holding its breath. One of the most striking recordings is of the Martian wind. It is not a roaring gale or a howling storm, but a low, soft hiss, like air moving gently through a narrow space. On some days, gusts sweep over the rover, and you can hear a faint rise and fall in pitch as they pass. These sounds carry a strange intimacy, not the grand, cinematic winds of science fiction, but something far more real, the quiet whisper of an alien atmosphere moving across rock and dust. Occasionally, Perseverance's microphones have picked up the sound of the rover itself, the creak of its wheels turning, the crunch of dust and gravel under its weight, the subtle rattle of its instruments adjusting. On Mars, these mechanical noises are surprisingly subdued. This is because sound travels differently here. The Martian atmosphere is incredibly thin, less than 1% the density of Earth's. It is also made mostly of carbon dioxide rather than nitrogen and oxygen. That combination changes the way sound waves move, making them travel slower and dampening higher-pitched tones. If you were standing next to someone speaking on Mars without a spacesuit, you would hear their voice as softer and lower than on Earth, and it would take slightly longer for the words to reach you. In fact, different pitches travel at slightly different speeds here. This means that on Mars, sounds can subtly separate into their high and low parts as they move, an effect we never experience naturally on Earth. This thin atmosphere also means that sound fades quickly with distance. A noise that is clearly audible a few meters away might vanish entirely if you take just a few steps back. The idea of echoes in the Martian canyons or craters is tempting, but in reality they would be faint and strange, far less dramatic than on Earth. Beyond the wind and rover, there have been other fascinating sounds. The SuperCam instrument on Perseverance fires a small laser to study the chemistry of rocks. Each laser pulse produces a tiny snapping noise as it vaporizes a pinpoint of material. In the recordings, these snaps sound like distant static, each one a tiny clue about the minerals that make up Mars's surface. Dust devils, swirling columns of wind and sand, have also brushed past the rover. When one passes, the microphones capture a momentary increase in noise, a fluttering rush as grains of sand strike the rover's body. It is not unlike the sound of light rain hitting a tent, but with a dry, brittle texture to it. These brief encounters are among the liveliest moments in an otherwise hushed world. Even the thin air itself has a sound, though it is so faint it is almost beyond perception. Sensitive instruments can pick up the constant soft background hiss of the atmosphere. Not quite a breeze, but the sound of countless microscopic movements of gas molecules. On Mars, this is the closest thing to a background hum. Imagining yourself standing there, the experience would be unlike anything on Earth. The quiet would be almost physical, as though the air itself were too fragile to carry sound. Your own movements, the crunch of boots on gravel, the rustle of your suit, would be loud to you but quickly swallowed by the openness. The wind would be gentle in your ears, even when it carried enough force to move fine dust around your feet. And every so often, you might hear the faint tick of something striking a rock, perhaps a grain of sand carried from miles away. In a sense, Mars is not silent. It is selective. It allows only certain sounds to exist, and it gives them space. There is no crowd of competing noises, no constant wash of life and weather to fill every gap. What you hear is what is there, and nothing else. It is a reminder that sound is not just about what is made, but what is allowed to linger. These recordings from Perseverance have changed the way we imagine Mars. It is no longer just a place we can see, it is a place we can hear, and those sounds tell their own story. They speak of a thin, delicate atmosphere, a planet shaped by wind and dust, and a silence that has stretched for billions of years. It is a quiet, not of emptiness, but of patience, waiting for whatever might come next. For as long as humans have gazed at Mars, the question has lingered, is it alive? Not in the way Earth bursts with greenery and creatures, but in the quiet, hidden way that life can sometimes take root in the most unlikely places. For much of history, this question belonged to speculation and imagination, but in the 1970s, it finally stepped into the realm of experiment. In 1976, NASA's Viking 1 and Viking 2 landers touched down on the Martian surface. They were the first successful spacecraft to both land and send back images from the ground, but they carried something more ambitious than cameras. Each Viking lander had a set of biology experiments designed to test for the presence of life. These weren't microscopes searching for tiny Martian worms. Instead, they looked for signs of microbial metabolism, the chemical fingerprints of living processes. The experiments were clever. One involved adding nutrients tagged with radioactive carbon to a soil sample. If microbes were present and metabolizing the nutrients, they would release radioactive carbon dioxide gas, which the instruments could detect. Another heated the soil to see if it released gases that might indicate organic activity. The results? Confusing. One experiment seemed to give a positive signal, suggesting that something in the soil was breathing, but the others didn't match. The chemistry didn't quite fit what scientists expected from life. The more they studied the data, the more it seemed possible that the reactions were caused not by biology, but by unusual chemistry driven by Mars' environment. The Vikings left us with a puzzle. Had we seen the signature of alien microbes, or just the quirks of Martian soil under strange conditions? Decades later, the debate still hasn't been fully settled. Some researchers argue that the Viking results were indeed consistent with microbial life, while most remain convinced it was a chemical trick, the soil reacting with nutrients in ways that mimic biology, but are purely chemical. In the years since Viking, our approach has become more cautious. Instead of going straight for the "is it alive" question, missions like the Mars rovers have focused on was it ever habitable? That means looking for liquid water in the past, organic molecules, and environmental conditions where life could survive, and over time, we've found compelling hints. One of the most intriguing modern clues comes from methane. On Earth, methane is often produced by living things, everything from microbes in the guts of animals to deep-sea bacteria that thrive without sunlight. It can also be produced by geological processes, like the reaction of certain minerals with water. In the thin Martian atmosphere, methane is unstable. Sunlight and chemical reactions break it down in a few hundred years. That means if we detect methane on Mars today, it must be coming from somewhere active, either geological or biological. Methane plumes have been reported by spacecraft orbiting Mars and by rovers on the surface. In 2003, the European Space Agency's Mars Express orbiter detected a large plume in the atmosphere. Later, NASA's Curiosity rover also picked up seasonal variations in methane levels, with higher amounts in summer and lower in winter. This pattern could hint at processes tied to temperature, perhaps from underground sources. The tantalizing part is that on Earth, most methane is biological. The frustrating part is that methane alone can't tell us whether life is responsible. We know it can be made without biology, and on Mars we can't yet trace it directly to its source. It could be seeping out from ancient reservoirs trapped underground, produced by reactions deep in the crust. Or it could be the breath of microbes that have been hiding for billions of years in the Martian subsurface. Another difficulty is that Mars does not make things easy for life to leave evidence. On Earth, traces of ancient microbes can be preserved in rock for billions of years, but our planet is geologically active, with weather and plate tectonics mixing and burying the surface. Mars, by contrast, has a harsh surface where ultraviolet radiation, cosmic rays, and chemical reactions constantly destroy organic molecules. Even if life once thrived here, its remains could have been scrubbed away by the planet's chemistry. That's why so much attention is now on the subsurface. Just a few meters below the Martian surface, life would be shielded from much of the radiation. Liquid water could exist there in small amounts, locked in salty brines or warmed by underground heat. If life ever found a foothold, this is where it might have retreated when the planet dried out. Drilling to these depths is challenging, so far beyond the capability of our rovers, but it remains a tantalizing frontier. NASA's Perseverance rover, along with the European Space Agency's upcoming Rosalind Franklin rover, is focused on collecting rock samples from ancient river deltas and lake beds. These places are prime targets because on Earth, such environments are excellent at preserving microbial fossils. Perseverance is catching samples for a future mission to bring back to Earth, where they can be studied with the full arsenal of our laboratories. If those rocks hold microscopic fossils, they could finally answer the question. Even then, proving life exists, or once existed, is far from simple. In science, extraordinary claims require extraordinary evidence. For Mars, that means not just finding something that looks like a fossil, but showing beyond a reasonable doubt that it could not have been formed by chemistry alone. The history of the Viking results has made scientists wary of jumping to conclusions too quickly. The search for life on Mars is in many ways a search for ghosts. We're looking for things that may not be here anymore, the chemical whispers, the geological shadows of a biosphere long gone. It could be that life arose on Mars in its warm, wet youth and vanished without leaving much behind. It could also be that it never emerged at all, and that the conditions we see as promising were never quite enough. Or perhaps, and this is the most haunting possibility, life is still there, not in the open, but deep underground, in pockets of water and warmth biding its time. The mystery endures because Mars offers just enough to keep the hope alive. It is not a dead rock in the same way as Mercury or our moon. Its surface tells a story of change, of water, of chemistry, of energy. All the ingredients that on Earth seem to lead inevitably to life. Whether Mars ever made that leap is still the great unanswered question. And when the answer finally comes, it will not just change our understanding of Mars, it will reshape the way we see life's place in the universe. Long before we had the technology to make it possible, people imagined walking on Mars. Early visions of Martian colonies appeared in science fiction of the 19th and early 20th centuries, when writers painted vivid pictures of domed cities under dusty skies, canals flowing with water, and exotic alien landscapes. In those days, Mars was still a mystery, its surface blurred in telescopes and its nature open to speculation. The idea of humans living there was as much fantasy as science, but it planted a seed in the human imagination that has never stopped growing. As our knowledge of the red planet increased, the fantasies began to merge with engineering reality. By the mid-20th century, serious scientists were sketching out plans for crewed missions to Mars. Visionaries like Wernher von Braun proposed enormous spacecraft carrying teams of astronauts for long stays on the surface, while others imagined fleets of ships ferrying settlers to begin building permanent outposts. In these early concepts, the biggest hurdle was simply getting there, a months-long journey through deep space, relying entirely on life support and careful planning. Today, the dream has evolved into something more tangible. Space agencies and private companies have drawn up detailed mission plans, and rovers have scouted potential landing sites. We know far more about what a human crew would face, and the list of challenges is daunting. One of the most serious threats is radiation. On Earth, our thick atmosphere and strong magnetic field shield us from most of the sun's harmful particles and the cosmic rays streaming in from deep space. Mars, with its thin air and absent magnetic field, offers almost no such protection. Astronauts would be exposed to radiation levels far higher than on the International Space Station, raising risks of cancer and other health issues. Shielding habitats with thick walls, burying them under Martian soil, or building them inside natural caves could help, but all of these solutions require considerable effort and resources. Then there is the dust, fine, iron-rich particles that coat the planet's surface. Martian dust is not just a nuisance, it is electrically charged, clingy, and possibly toxic due to compounds called perchlorates. It can clog machinery, scratch spacesuit visors, and irritate lungs if it somehow finds its way inside a habitat. Keeping it out would require careful suit designs, airlock systems, and constant maintenance. Isolation would be another heavy burden. A crew on Mars would be farther from home than any humans have ever been. Communication with Earth would have a delay of several minutes each way, meaning conversations could never be real-time. If something went wrong, there would be no quick rescue. The crew would be on their own, with only the tools and knowledge they brought. The psychological toll of such remoteness, combined with the monotony of a barren landscape, could be as challenging as any technical problem. Low gravity adds yet another layer of complexity. Mars's gravity is about 38% of Earth's, and while that might make carrying heavy equipment easier, we do not yet know how the human body will respond to living long-term in such an environment. Extended stays in microgravity cause muscle and bone loss, as well as changes in vision and circulation. Whether Mars' partial gravity would prevent or merely slow these effects is still an open question. Yet despite these formidable obstacles, the pull of Mars remains strong. Imagining the first human day on the Red Planet is enough to stir excitement in even the most cautious minds. Picture stepping out of a lander onto dusty soil that has never known a human footprint. The sky overhead is a butterscotch colour, the sun smaller and dimmer than you have ever seen. The air is thin and unbreathable, but through your helmet you feel the stillness, a quiet deeper than anything on Earth. Your first steps feel light, almost like slow motion. Each stride sends up a small puff of rust-coloured dust that hangs in the weak gravity before settling back down. You might turn in place, taking in the vast emptiness, jagged hills in the distance, a horizon farther away than it seems thanks to the planet's smaller size. The cold is sharp, even through layers of insulation, and you know that survival here will depend entirely on the technology keeping you alive. Inside your habitat, the atmosphere is warm and Earth-like. Outside the thick walls, it is a freezing desert at -60 degrees Celsius on average. Every system, from oxygen recycling to water recovery, has to work flawlessly. You drink coffee made from water melted from ice mines nearby, or perhaps extracted from the very air. Each sip tastes like history in the making. Work begins quickly. Instruments are set up to measure weather, monitor radiation, and study the soil. Solar panels unfold to catch the weak sunlight, and perhaps a small greenhouse begins sprouting the first Martian-grown plants. You're part of an experiment unlike any other, not just scientific research, but the trial run of a human foothold on another world. As night falls, the temperature plunges even further, and the stars appear with piercing clarity. Phobos and Deimos, the two tiny moons, drift overhead. You might pause to think about the millions of kilometers between you and Earth, the impossibility of stepping outside without a suit, the delicate bubble of life around you. And yet, in that fragile bubble, there is also the most remarkable fact of all: humanity. is here. In that moment, you understand why generations have dreamed of this day. It is not just about exploring another planet, it is about proving that life can take root beyond its birthplace, that our story is not confined to one world. The challenges are immense, the risks real, but the view from that alien soil makes it clear why we will keep trying until it happens. Before human boots ever touch the soil of Mars, our mechanical emissaries have already been there for decades. They have no lungs to breathe its thin air, no eyes to see the butterscotch sky in the way we would, yet they have been our explorers, our photographers, and our geologists. The story of Mars exploration is one of patient, persistent visits, each mission building on the discoveries of the last, until the red planet began to feel less like a distant light in the sky, and more like a familiar, if mysterious, neighbour. The earliest visits were brief and cautious. In the 1960s and 70s, spacecraft like Mariner 4, 6 and 7 performed quick flybys, snapping the first close-up images of Mars. What they sent back was startling, a cold, cratered world that looked, at first glance, much like the Moon. It was a sharp contrast to the canals and oases some had still imagined. Mariner 9, arriving in 1971, changed that picture dramatically. It became the first spacecraft to orbit another planet, and as the global dust storm of that year began to settle, it revealed towering volcanoes, vast canyons, and dry river channels. Mars was suddenly a far more interesting place. Then came the first attempts to land. The Viking missions of 1976 were marvels of engineering. Viking 1 and 2 not only touched down safely, but also carried out experiments to look for signs of life. The results were ambiguous, sparking debates that continue to this day, but the missions proved that a controlled landing and long-term operations on Mars were possible. After a long pause in Mars exploration, the late 1990s marked the start of a new era. This was the age when our explorers began to roll across the Martian surface. The first rover, Sojourner, arrived in 1997 as part of the Pathfinder mission. Small, slow, and endearingly cautious, it was the robotic equivalent of a toddler taking its first steps, and those steps proved we could navigate the rugged terrain. But it was in 2004 that Mars received two of its most beloved visitors, Spirit and Opportunity. These twin rovers were designed to last 90 days, but they quickly showed they were not bound by such modest expectations. Spirit explored for over 6 years, climbing hills and weathering fierce dust storms before becoming trapped in soft soil. Opportunity, meanwhile, outlived its sibling by a staggering margin, roving tirelessly for nearly 15 years. It travelled more than 45 kilometres, sending back panoramic views, mineral evidence of ancient water, and a steady stream of quiet determination. When its final message arrived in 2018, it was poetic in its simplicity. The skies had darkened in a global dust storm, and the rover had gone silent. Engineers described its last communication as "my battery is low and it's getting dark." Though not literally what the rover said, the sentiment captured the hearts of millions. In 2012, Curiosity arrived, bringing with it a new level of sophistication. This nuclear-powered rover was larger than a small car, bristling with cameras, drills, and laboratories. It was tasked with determining whether Mars had ever been capable of supporting microbial life, and it quickly found evidence in the form of ancient lake beds and clay minerals. Curiosity also carried a sense of personality. Its social media updates and images of itself against alien backdrops gave the mission a human-like charm. It remains active to this day, slowly climbing the slopes of Mount Sharp, piecing together the planet's environmental history layer by layer. Then came Perseverance in 2021, the most advanced rover ever sent to another world. Landing in the Jezero crater, an ancient river delta, it was specifically tasked with the search for signs of past life. It drills into rock, caches samples for a future mission to bring back to Earth, and even brought along a small helicopter named Ingenuity. Originally planned to fly only a handful of times, Ingenuity has now completed dozens of flights, becoming the first aircraft to operate on another planet. Together, Perseverance and Ingenuity have given us moving images of a Martian landscape from both ground and air, a perspective that no telescope could ever match. Orbiters, too, have played an essential role in this story. Spacecraft like Mars Odyssey, the Mars Reconnaissance Orbiter, and the European Space Agency's Mars Express have mapped the planet in exquisite detail, revealing seasonal changes, monitoring dust storms, and scouting for potential landing sites. Their high-resolution images have allowed us to walk the surface virtually, tracing dried riverbeds or zooming in to see the wheel tracks left by our rovers. Each mission has its own character. Spirit was the determined pioneer, battling the odds until the very end. Opportunity was the loyal marathoner, quietly breaking records and expectations alike. Curiosity is the curious scientist still poking and prodding the landscape for answers. Perseverance is the ambitious trailblazer, gathering treasures for a future return to Earth. And orbiters are the watchful companions overhead, always keeping a steady eye on the dusty surface below. What they have shown us goes far beyond what any telescope could reveal. We have seen frost forming on sand dunes at dawn, delicate ripples in the soil shaped by Martian winds, and sunsets that fade from blue to pink in a way no Earth sky ever could. We have watched dust devils dance across the plains, caught glimpses of tiny pebbles that have lain undisturbed for millions of years, and seen the layered cliffs of canyons carved by forces we are only beginning to understand. Through them, Mars has transformed from an abstract red dot to a place we can almost imagine walking across. These mechanical explorers have been our eyes, ears, and hands on a distant world, each one a chapter in an ongoing story. One day, human explorers will add their footprints to the wheel tracks, but even then, the rovers, landers, and orbiters will remain the quiet pathfinders that first opened the way. If you were to tune into a daily weather forecast on Mars, the presenter would probably have a permanent look of mild concern. The first number on screen would be the daytime high, perhaps a comfortable sounding 20 degrees Celsius near the equator in summer. But then the nighttime low would appear, plunging to -70 or even lower, and you'd start to rethink your outdoor plans. This is a world where temperature swings can be brutal, not just from season to season, but from one side of the day to the other. With such a thin atmosphere, there is very little to trap heat once the sun dips below the horizon. That thin air, made mostly of carbon dioxide, also changes the way wind works. On Earth, even a moderate breeze can be felt pushing against you, but on Mars, the air is so rarefied that a 100-km/h wind wouldn't knock you over. You might feel it as a faint push on your suit, but the dust it carries could still be a problem, because the dust is everywhere. This is a planet where fine particles of iron oxide can drift and settle in every crevice, and where dust devils, towering columns of swirling grit, wander across the plains like slow-moving ghosts. Some of these whirlwinds are just a few meters across. Others can stretch hundreds of meters into the sky, leaving dark tracks on the ground as they pass. Mars does have seasons, though they are different from ours in both length and character. The planet is tilted on its axis by about 25 degrees, very similar to Earth's 23.5, which means it experiences a familiar pattern of changing sunlight. But because Mars takes nearly twice as long to orbit the Sun, each season lasts roughly twice as long as it does on Earth. A Martian summer is not necessarily warm, unless you're standing near the equator at midday, but it can still bring enough sunlight to melt carbon dioxide frost at the poles, releasing it into the atmosphere. Winters, on the other hand, are long, cold and dry, with polar caps growing in size as frozen carbon dioxide and water ice accumulate. One of the more surprising aspects of Martian weather is how dynamic it can be despite the planet's calm appearance from afar. Global dust storms can engulf the entire world, reducing sunlight to a dim orange glow for weeks or months. These storms are not necessarily violent at the surface, but they can block enough sunlight to threaten solar-powered equipment, as Opportunity learned in its final days. In less dramatic times, the sky may be clear enough to reveal a pale sun by day and an almost star-filled sky by night, and then there are the sunsets. On Earth, we are used to fiery reds and oranges when the sun dips below the horizon. Mars does the reverse. Thanks to the way fine dust particles scatter light, Martian sunsets often appear bluish at the very centre, with a halo of pale gold or butterscotch surrounding them. The effect is caused by the dust scattering blue light more efficiently in the direct path of the sun, while allowing the redder wavelengths to be scattered away. It means that the close of day on Mars carries a strange, almost dreamlike quality, as if the planet is reminding you that it plays by its own rules. The daily rhythm here is an interplay of extremes: heat and cold, calm and wind, light and dust. A day, or sol, on Mars lasts just over 24 hours, so in that respect it feels almost familiar. But the weather it contains is shaped by a world with too little air to hold its warmth, too much dust to keep its skies perfectly clear, and just enough tilt to create long, drawn-out seasons. Standing under that thin sky, with the faint hiss of wind in your ears and the horizon fading into muted colours, you might find that Mars weather is less about comfort and more about quiet endurance, a constant reminder that this is a world shaped by patience and time. If you were to look at Mars and imagine it covered in oceans and forests, you'd be venturing into the realm of one of humanity's most audacious ideas: terraforming. It's the concept of taking a frozen, airless desert and turning it into something more Earth-like, a place where humans could live without spacesuits and where plants might take root under a breathable sky. The vision is bold, romantic, and, at least for now, still a long way from reality. The starting point for any plan is Mars' atmosphere, or rather the lack of it. The air here is thin, about 1% of Earth's sea level pressure, and made mostly of carbon dioxide. To make it habitable, we'd need to thicken that atmosphere considerably. One idea is to release greenhouse gases, trapping heat and raising the temperature until frozen carbon dioxide and water ice on the planet's surface and subsurface begin to vaporize. This could, in theory, create a chain reaction where warming releases more gases, further increasing the pressure and temperature. The end goal would be an atmosphere thick enough to support liquid water and comfortable temperatures, at least comfortable in comparison to the current -60 degrees Celsius average. Science fiction has long embraced dramatic versions of this process. In stories, giant orbital mirrors focus sunlight onto the poles, melting ice caps and turning them into seas. Massive machines pump gases into the air, and within a few decades lush valleys appear where there were once barren plains. Reality, however, is far more stubborn. Research suggests that even if we used every scrap of accessible carbon dioxide on Mars, we might still not get enough to create a stable, breathable atmosphere. Without a magnetic field to protect it, any thickened atmosphere would also slowly leak into space under the constant pressure of the solar wind. There are smaller scale approaches that don't try to transform the entire planet, but instead focus on creating pockets of habitability. These could be enormous domes or underground cities where the air is controlled and temperatures are regulated. Such para-terraforming sidesteps some of the enormous challenges of changing the whole planet, though it also lacks the romantic appeal of standing outside under an open Martian sky without a helmet. Beyond the technical hurdles, there's the question of whether we should do it at all. Terraforming would be irreversible. If Mars harbours microbial life, even deep underground, transforming the planet could wipe it out or alter it beyond recognition. In a way, it would be taking the only example of an untouched Mars and replacing it with something more familiar to us, perhaps at the cost of losing a unique chapter of cosmic history. Some argue that we have a moral responsibility to preserve Mars as it is, at least until we know for certain whether it has its own native life. Others see terraforming as part of a longer-term survival strategy for humanity. If Earth were ever to become uninhabitable, a green Mars could serve as a second home. This perspective treats the planet not just as a scientific curiosity, but as a backup, a kind of planetary insurance policy. Between these two views lies a complicated mix of ethics, ambition, and practicality. Even the most optimistic projections suggest that turning Mars from red to green would take centuries, if not millennia. In that timescale, our technology, our values, and perhaps even our species could change dramatically. It's possible that by the time we have the tools to do it, we might decide we no longer want to, or that we'd rather explore and adapt to Mars as it is instead of forcing it to change. For now, terraforming exists in a strange space between scientific possibility and science fiction. It's a thought experiment that forces us to consider what it means to reshape another world, not just in terms of engineering, but in terms of philosophy. Mars is a place that has existed for over 4.5 billion years without our intervention. Whether its next chapter is written in green or left in its natural shades of red may say as much about us as it does about the planet itself. Long before spacecraft sent back images of dusty plains and cratered horizons, Mars existed in the human imagination as a place of power, mystery and, more often than not, conflict. Its rusty colour, visible even to the naked eye, seemed to link it to the hue of blood, and across many cultures this association led to its role as a god of war. For the Romans, Mars was second only to Jupiter in importance, a protector of Rome itself and a symbol of military might. His Greek counterpart, Ares, was more chaotic and unpredictable, often portrayed as brash and quarrelsome. Other civilizations wove Mars into their own myths. In Babylonian astronomy, it was Nergal, a deity of war and plague. In Hindu tradition, Mangala, a god associated with strength and conflict. Even in places where Mars wasn't explicitly a war god, it carried an aura of danger and intensity. This symbolic weight carried forward into the modern era, influencing not only mythology, but also literature. In the late 19th century, telescopes had improved enough that astronomers could make out tantalizing details on Mars's surface. Dark markings, bright polar caps, and what some swore were long straight lines. The Italian astronomer Giovanni Schiaparelli called these features canali, meaning channels, but English translations rendered it as canals, igniting the idea of artificial waterways built by an intelligent race. That single linguistic twist fed decades of speculation and stories. H.G. Wells seized the idea and ran with it in The War of the Worlds, published in 1898, where Martians, desperate for resources, invade Earth. His alien antagonists were a reflection of both the imperial ambitions and the technological anxieties of the time. The story was later adapted by Orson Welles for radio in 1938, causing panic among some listeners who thought the invasion was real. While the actual scale of the panic was smaller than the legend suggests, it cemented Mars as a symbol of the unknown and potentially threatening other. In the early 20th century, the idea of a dying Mars, inhabited by an ancient but fading civilization, flourished in pulp fiction. Edgar Rice Burroughs' Barsoom series, starting with The Princess of Mars in 1912, depicted a desert world of strange cities, warring tribes, and heroic adventures. Ray Bradbury later took a different approach in The Martian Chronicles, painting Mars as a hauntingly beautiful place, tinged with loss and nostalgia, where human settlers wrestle not only with the landscape but with their own nature. Outside of fiction, Mars mania took hold in the public imagination. Observatories opened their domes to curious crowds eager to glimpse the red planet for themselves. Newspapers and magazines speculated about Martian life, sometimes blending fact and fancy so freely that readers could hardly tell where one ended and the other began. Even serious scientists entertained the possibility of vegetation and seasonal changes caused by melting ice caps. Each opposition of Mars, when the planet came closest to Earth, brought fresh bursts of speculation and artistry. This cultural fascination shaped more than books and films. It seeped into music, art, and even the names of places. Composers like Gustav Holst, captured Mars' warlike associations in orchestral form, while visual artists used its stark landscapes as backdrops for scenes of alien wonder or menace. In many ways, Mars became a mirror for human hopes and fears, a canvas on which to project our anxieties about scarcity, our curiosity about life beyond Earth, and our desire for adventure. Today, while robotic explorers have stripped away much of the mystery, Mars still holds a place in the cultural imagination. It's no longer a world of certain canals or inevitable invasions, but it remains a stage for our storytelling, a reminder that sometimes the journey to another planet begins not with a rocket, but with a glance upward and a spark of curiosity. Over the coming century, Mars will likely transform from a distant point of light in our night skies into a far more familiar place, not necessarily because it will change, but because our presence there will. Space agencies and private companies are already sketching out plans that, a few decades ago, would have belonged purely to science fiction. These range from robotic supply chains to permanent human outposts, with timetables that imagine footprints in the red dust within the next few decades. Whether those timetables hold is another matter entirely. Space history has a habit of proving that bold predictions often need a little more time. In the short term, the next generation of Mars exploration will almost certainly involve more sophisticated robots. New rovers may travel further, drill deeper, and perhaps even begin the first steps of returning samples to Earth. That idea alone, holding Martian rocks in a laboratory here on our planet, has the potential to rewrite what we know about Mars geology and its potential for life. Orbiters will continue to map the surface in ever higher resolution, revealing the subtle changes in dunes, frost, and atmospheric dust. The planet's weather will be monitored like a quiet neighbour's garden, noting every gust and frost pattern. Human missions will be the Great Leap. A crewed voyage to Mars is often described as the next giant leap after the Moon, but the scale of the challenge is almost unimaginable. The round trip could take close to 3 years, with astronauts living and working in a confined environment, exposed to cosmic radiation and far from any hope of immediate rescue. The landing itself is its own engineering puzzle. Mars' thin atmosphere makes it too light to slow heavy spacecraft efficiently with parachutes alone, yet too thick to simply ignore aerodynamic forces. Solving this will be one of the defining technical hurdles. If humans do land, the question becomes, do we stay? An initial mission might last only weeks or months, but establishing a sustained presence would require life support systems that can work for years with minimal resupply. Water could be extracted from buried ice or from the atmosphere itself, oxygen from carbon dioxide, and food from carefully managed greenhouses. Each of these is possible in theory, but doing all of them reliably on a cold, dusty world millions of kilometers away is a different matter. The more ambitious visionaries speak of colonies, entire communities living beneath domes or within shielded lava tubes, lit by artificial suns and warmed by nuclear power. In these scenarios, Mars becomes not just a science outpost but a second home for humanity, a place where new generations might grow up never having seen Earth's oceans or forests except in books and recordings. For some, this is an insurance policy against catastrophe on Earth. For others, it is an expression of our species' restlessness, our need to see what lies beyond the horizon. Yet there is also a quieter, more cautious vision of the future, one where Mars remains largely untouched, visited only by scientists and explorers, its landscapes preserved as they have been for billions of years. In this scenario, the red planet becomes something like Antarctica, a place of discovery, not settlement, valued for its unspoiled nature rather than its potential as a new frontier. There are strong arguments for this approach. Colonization would inevitably alter the planet's environment in ways we cannot fully predict, and if Mars harbours even the faintest traces of native life, our presence could overwhelm it. Over the next 100 years, we might see a blend of both paths. Robotic science bases may become permanent fixtures, even if human visits are rare and brief. Spacecraft may ferry samples, equipment, and perhaps even the occasional crew between the planets, gradually weaving Mars into the sphere of human activity without transforming it entirely. Whatever happens, our relationship with Mars will no longer be a distant fascination. It will be an ongoing conversation between two worlds. Perhaps a century from now, children will look up at the red dot in the sky and know that someone, right now, is walking there, looking back at a blue star in their own heavens. Or perhaps they will see it as we do now, remote, silent, and waiting. A neighbour who watches but never speaks. Both futures hold a certain beauty, and both remind us that Mars, in the end, will decide how much of itself it is willing to share. From the surface of Mars, Earth is not the sprawling, detailed world we know. It is a tiny, pale dot suspended in an ocean of black. Even through the sharpest lens or the clearest visor, it is nothing more than a speck. Bright enough to notice if you know where to look, yet small enough that you could hide it behind the tip of your finger. On some Martian nights, when the air is still and the dust settles, it gleams with a quiet steadiness, a pinprick of colour in the cold, thin sky. That dot is everything. Every mountain, every ocean, every song, every language, and every human who's ever lived. And from here, it feels impossibly far away. Earth, as seen from Mars, has a soft blue glow, sometimes tinged with white from the clouds swirling in its atmosphere. Through a telescope you might catch the faint outlines of continents, smudged and ever-shifting. The moon, our familiar companion, is there too, just as small, but tethered to the Earth like a loyal friend, trailing it across the Martian sky. Together they drift from one horizon to the other, a reminder that home is not just one world but two. The distance between Mars and Earth changes constantly. At their closest, they are roughly 34 million miles apart, at their farthest over 200 million. Those numbers are hard to truly grasp. Even a radio signal, moving at the speed of light, can take anywhere from 3 to over 20 minutes to travel the gap. Imagine speaking to someone you love and waiting for nearly half an hour to hear them reply. That delay turns conversation into something almost ceremonial. Each word chosen with care, each pause heavy with longing. Standing on Mars and looking at that faint blue dot, the mind can't help but wonder. You realise that from this distance there are no borders, no divisions. Politics, rivalries, and everyday worries shrink to invisibility. The only thing you see is a shared home, fragile and finite, hanging in the darkness. It's a perspective that astronauts have described from low Earth orbit, the overview effect. But from Mars, that effect must be amplified 100-fold. Here the separation is so vast that Earth seems less like a place and more like a memory. There's also a quiet ache in seeing it this way. The landscapes of Mars are alien, red dust, jagged rocks, and a horizon that seems endless. There are no forests swaying in the wind, no oceans roaring against cliffs, no familiar birdsong at dawn. The sight of Earth in the sky becomes a tether to all of that, a reminder that warmth, water, and life itself are not universal. That pale dot is where rain falls, where rivers run, where green stretches beyond the horizon. And here, all of that is absent. The contrast is sharp enough to make you hold your breath. Some scientists and mission planners have reflected on the psychological weight this could place on the first humans to travel here. Mars is not just physically distant, it is emotionally distant. Once you are here, you cannot simply return if you feel homesick. The journey back is months long, and that's if everything goes perfectly. The view of Earth in the night sky would be both a comfort and a torment, a reminder that home exists, but also that it is almost unimaginably far away. And yet, there is something deeply humbling about that perspective. You're reminded that in the vastness of the solar system, Earth is small, delicate, and rare. From here, it is not the centre of everything. It is just one of many points of light. You begin to see it as a single living organism, a fragile sphere wrapped in a thin shell of air, drifting through space. You understand, perhaps more deeply than ever before, how easily it could change and how much care it needs to survive. It also stirs a kind of kinship with Mars itself. Standing on its surface and seeing Earth as a faraway jewel, you may start to feel that the two worlds are part of the same family, siblings with different stories. One is green and warm, the other red and cold, yet both circle the same sun, shaped by the same cosmic forces. You might even imagine what Earth would look like from Jupiter or Saturn, another distant point in the same starfield. The realization settles in. The universe is vast, and even our home is just a chapter in a much larger book. For those who would live and work on Mars, the view of Earth could become a ritual. Perhaps at the end of a long day, after repairing equipment or studying rocks, someone might step outside in their suit, look up, and find that familiar glimmer. The sight might carry them through the months of isolation, reminding them why they came and what they are working toward. That little dot could represent family, friends, and the entire shared history of humankind, all carried in a single point of light. The emotional pull of that view is hard to overstate. We are creatures who evolved to navigate by the sun and the moon, to see familiar constellations overhead. On Mars, many of those patterns are shifted, and the sky feels different. But there, among the unfamiliar stars, is something that belongs to you. Something that says, this is where your story began. And perhaps, after a lifetime of seeing Earth from this distance, the idea of home would change. Maybe it would no longer be a specific planet, but the connection between them. Earth as the cradle, Mars as the frontier, both part of a shared human journey. Looking back across millions of miles, you would see not just a blue dot, but the seed of everything you know, set against the infinite night, yet shining just brightly enough to find again. Mars is quiet in a way that is almost beyond imagining. Not the sort of quiet you find in a library or on a still winter morning, but a silence that is woven into the air, or rather, into the near absence of it. Even the moon, stark and airless as it is, doesn't carry quite the same weight of isolation. The moon is close enough to Earth that it always feels tethered to home. Mars is not. It hangs alone in the cold, thin light of the sun, and standing there, if you ever could, you would feel the gap between you and every other living thing more keenly than anywhere else in the solar system. Part of what makes Mars feel lonelier than the moon is the sheer distance. The moon is a short cosmic step away, a place you can reach in a matter of days. Radio messages bounce back in seconds. Mars is another story entirely. At its closest, it takes several minutes for a signal to travel between Mars and Earth. At its farthest, nearly a quarter of an hour passes between you sending a word and getting a reply. That delay is enough to turn conversation into something more like letter writing. Slow, deliberate, with no way to share the small, fleeting moments of your day in real time. The moon also has the comfort of familiarity. Stand on its surface and you can see Earth hanging in the black sky, huge and bright, like a guardian lantern you can never lose sight of. On Mars, Earth is reduced to a pale speck, just another dot among the stars. It's visible, yes, but only if you know exactly where to look, and even then it feels fragile. A bead of light that could vanish with the slightest blink. That alone changes the emotional weight of being there. Psychologically, the difference is profound. Humans evolved in close-knit groups, dependent on constant contact with others. Mars strips that away. Even if you were surrounded by a small crew, the planet itself would feel indifferent to your presence. Its vast landscapes seem to stretch on forever, empty and unbroken. Walk in any direction, and you might not encounter a single sign of life. No plants, no birds, not even the hum of insects. The air is too thin to carry the bustling noise of life as we know it. The silence is almost physical, like a blanket pressed against your ears. And yet there's beauty in that stillness. With no rustling leaves, no trickle of water, and no hum of machinery except the ones you bring, your awareness sharpens. You notice the crunch of your boots on the gritty soil. You hear your own breathing loud inside your helmet. You might even pick up the faint, ghostly whisper of wind moving over the rocks. Not the wild, rushing winds of Earth, but a softer, thinner sigh that has crossed the same ground for millions of years. Some explorers imagine that kind of silence would be unsettling, even oppressive. But others think it could be almost meditative, a space where the mind can wander without distraction. There's a strange comfort in knowing that the planet won't rush you. Nothing here grows or decays at human speed. Mars moves on its own clock, slow and steady, shaped by dust storms and seasons that take twice as long as ours. There's also the thought that this silence is ancient. It existed long before any ear could hear it and will last long after. The wind over Martian plains has carried the same song, if you could call it that, for billions of years, sometimes burying craters under dunes, sometimes revealing them again. Every sound here is part of that unbroken history, tiny and fleeting compared to the scale of the place. In that way, Mars offers something that's hard to find back on Earth, the feeling of standing outside time. On Earth, even the most remote places carry some trace of life. A bird's call, a distant aircraft, the rustle of grass in the breeze. On Mars, the landscape doesn't acknowledge you. It doesn't change because you're there. It's like opening a door to a room that's been locked for eons, the air inside untouched, the furniture, if there were any, exactly as it was left. It's easy to imagine the psychological toll of that kind of isolation over months or years. Humans rely on variety, sights, sounds, smells, to anchor themselves in reality. Without them, time can start to blur, and small problems can grow in the mind. Astronauts would need to find ways to create their own rhythms, their own sources of noise and movement, just to keep from being swallowed by the stillness. But there's another side to it. For some, the silence could be a gift. It could strip away the constant chatter of modern life, the notifications, the background hum of engines and electricity. In that emptiness, you might find space to think deeply, to feel the scale of the universe more keenly than ever before. Standing on Mars, under its faint salmon-coloured sky, with only the soft hiss of your oxygen supply for company, you might finally understand how vast and ancient the cosmos truly is, and how small yet precious our little blue home is within it. Mars's silence is not the silence of absence. It's the silence of a place content to exist without interruption. It's a reminder that life is not the default state of the universe. It's the exception. And in that rare stillness, there's a kind of poetry, a reminder that even the loneliest corners of the cosmos can hold their own quiet beauty. Mars is more than rock and dust and cold, thin air. It is a place where science, mystery and poetry meet in a way few other worlds can offer. Every image, every spectrum reading, every seismograph trace tells a story, some of them millions or billions of years in the making. We read these stories in the swirl of its dust storms, in the dry scars of rivers that once flowed, and in the faint chemical whispers that hint at the possibility of a life. Each discovery is a line in a cosmic diary that we're only just learning to read. The science of Mars is exacting. We measure its air pressure down to fractions of a pascal, chart the mineral content of rocks with lasers, and map its surface in detail so fine we can trace the paths of individual boulders. We know its iron oxide-rich dust is the reason for its iconic red colour. We understand that its mountains rose in slow-motion eruptions over millions of years, and that its great canyons open not from the rush of a single river, but from tectonic strains and geological shifts that split the crust wide open. And yet, the more we learn, the more questions crowd in to take the place of the ones we've answered. The mystery lies in what Mars refuses to tell us. Was it once a blue-green world with seas and rivers like ours? Did microbial life stir in those waters, clinging to warm rocks or thriving in mineral-rich shallows? If so, did it die out when the atmosphere faded, or does it still hide deep underground in briny pockets, beyond the reach of our instruments? Even the methane we occasionally detect is a puzzle. It could be the breath of ancient microbes or just a quirk of chemical reactions in the rock. Mars gives us just enough to keep us intrigued, never enough to settle the debate. And then there's the poetry, the part of Mars that refuses to fit neatly into data tables. There's poetry in the way its pale blue sunsets stretch across a salmon-coloured sky, in the patient dance of its two misshapen moons, one inching ever closer to a slow and inevitable demise, in the sight of frost forming on a dune under a canopy of alien stars. Mars doesn't just invite us to study it, it invites us to feel something. Wonder, awe, perhaps even kinship. As much as Mars is a destination in its own right, it is also a mirror. In studying its geology, we better understand our own planet's story. Its dry riverbeds are echoes of our own flowing waters. Its volcanic peaks are frozen portraits of forces that still shape Earth today. Its loss of atmosphere is a cautionary tale, a reminder of how fragile a planet's habitability can be. Every image we send back from Mars is also a reflection, not of ourselves as individuals, but of humanity as a whole, reaching outward, seeking to know. When we look at Mars, we also see our own drive to explore. We see centuries of dreamers and thinkers who imagined stepping onto its dusty plains long before rockets ever left the ground. We see the merging of hard science with imagination, a rare alchemy that keeps us reaching further into the cosmos. In the end, the journey to Mars is not just about physics and engineering, it is about curiosity. The same curiosity that once led humans to cross oceans now leads us across the void between worlds. There is also a quiet humility in Mars. It reminds us that the universe does not bend to our timelines. We can plan missions and send rovers, but Mars rotates, orbits, and changes at its own pace. It does not hurry for us, nor does it linger. That indifference is strangely grounding. It tells us that our explorations, for all their ambition, are small steps in a much larger cosmic dance. One day, perhaps, humans will walk there. They will stand under its pale sun and feel the crunch of its dust beneath their boots. They will see Earth not as a sprawling blue and white globe, but as a distant pinprick of light. And when they do, they will carry with them the long chain of stories, the river valleys mapped by orbiters, the first panoramic mosaics from Viking, the wheel tracks of spirit and opportunity, the rock samples collected by perseverance. Every discovery will be a chapter in a shared human narrative that stretches back to the first time we looked up at the night sky and wondered what those red sparks might be. Closing the long journey to Mars is not about placing a final period at the end of the sentence. It is about standing back from the page and seeing the story as a whole, a story still being written, still shifting with every new measurement and every new photograph. Science will keep asking its questions, mystery will keep guarding its secrets, and poetry will keep finding its way into the quiet spaces in between. In the end, perhaps the most remarkable thing about Mars is the way it draws all these threads together. It is a planet, a puzzle, and a poem, a place both utterly alien and strangely familiar, a reminder of what we have learned and of how much more there is to discover. And as we step away from it, for now, we can carry with us the stillness of its deserts, the sweep of its canyons, and the faint promise that somewhere, out there in the silence, Mars is waiting for us to return. Mars, in all its dusty silence, has been more than just a destination for our machines and our imaginations. It has been a teacher. It has reminded us with every photograph and every spectral reading that worlds are fragile, histories can be erased, and survival is never guaranteed. Its surface is an open archive, a place where the chapters of planetary life are laid bare, some written in flowing rivers, others in the deep scars of impacts, and still others in the whisper of an atmosphere slowly slipping away into space. If Earth is a lush, dynamic novel still in the middle of its story, Mars is the weathered, ancient book on the neighbouring shelf. Its pages faded, some torn, others left blank. Looking at it, We see what happens when a planet loses its protective layers, when warmth bleeds away and time is left to work without interruption. In this way, Mars does not just tell us about itself, it warns us about our own world, about the delicate balances that keep seas liquid, air breathable, and life thriving. It also shows us that change is the only constant. 4 billion years ago, Mars may have been warmer, wetter, and more familiar to our eyes. Over time, it transformed into the dry, frozen desert we know today. The rivers dried, the seas vanished, the magnetic field went quiet. Life, if it ever began, was forced to retreat into the shadows or disappear entirely. We see, in that transformation, the long arc of planetary time, far longer than any human lifespan, far more patient than any human plan. In that patience, there is perspective. Our daily worries, our short-term struggles, even the centuries-long sweep of human history are but moments compared to the slow drift of continents or the gentle cooling of a world. Mars reminds us that change comes for everything, and yet there is beauty in what remains. The dunes ripple in patterns carved by wind that has blown for millennia. The mountains, though silent now, still rise with impossible grace into the thin sky. The polar caps breathe with the seasons, exhaling frost into the long Martian winter. There is also a strange kinship to be felt here. Mars is barren, but not dead in spirit. It holds traces of motion and possibility. It is not a blank rock, but a place with memory, a place that wears the marks of water's touch, of volcanic fire, of impacts from worlds beyond. Studying it feels almost like tracing the history of an ancestor whose life was very different from ours, but whose story still shaped us. From another angle, Mars also teaches humility. It's easy to imagine we could one day shape it to our needs, warm its air, fill its lakes, turn its rusty plains green. But the more we learn, the more we realize how immense the challenge truly is. It is a reminder that worlds are not easily tamed, and that sometimes the value lies not in changing them, but in listening to what they already have to tell us. That listening has given us more than scientific data. It has given us a new way of looking at ourselves. When our rovers send back images of the pale blue dot in Mars's sky, it is impossible not to feel a tightening in the chest. From that vantage point, Earth is fragile. Its oceans are hidden beneath clouds, its forests invisible, its cities reduced to nothing at all. All that we are, our history, our cultures, our languages, our loves and losses, exists on that small point of light. Mars makes us see home with fresh eyes, the way distance sharpens appreciation. And then there is the quiet, the kind of quiet that is impossible to find on Earth. No hum of insects, no crash of waves, no rustle of leaves, only the whisper of thin wind across rock and dust. That silence has a weight to it, but not an oppressive one. It is the silence of a world that has been left to itself for eons. It is a silence that invites you to breathe slowly, to let the mind wander, to imagine the centuries stretching out behind and ahead without rush. That stillness, oddly enough, is part of Mars' gift to us. In a world so noisy and fast, Mars asks us to slow down, to look closely, to recognize that meaning can be found in the smallest of details. The curve of an ancient riverbank, the layering in a cliff face, the frost etching a rock at dawn. It shows us that survival is not always about conquest or dominance, but about endurance. Mars has endured, not in the way Earth has, with flourishing life and restless geology, but in a quiet, steadfast holding of its place in the solar system. Perhaps this is why Mars has captured our imagination for so long. It embodies both our curiosity and our longing. It is a reminder that we are explorers by nature, always drawn to the horizon, but also that the horizon is not just a place to reach. It is a place to reflect. In the centuries to come, we may walk there. We may plant shelters on its plains, send our own footprints into its dust. We may stand on its highest cliffs and watch Phobos skim across the sky, and when we do, we will carry with us not just the tools of science, but the stories, dreams, and quiet lessons that Mars has already given us. Until that day, Mars will remain as it is, a patient world, turning slowly under the sun, waiting. The red horizon will glow under thin light, and the long shadows will stretch across its valleys. The winds will sigh softly through the canyons, and somewhere, beyond the reach of that horizon, Earth will shine as a tiny blue spark in the darkness. Of years, and will wait for billions more